Dear colleagues, good morning. Today we are having a session on social network analysis. My name is Olessia Koltsova. I will be chairing this session. And so far as I understand, we have all the presenters here. So Evgeniia Shchepina. Hello.
Yes, hello.
Do we have Olga Gerasimova?
Yes, hello everyone. Do you hear me? Do you hear me?
Yes, we can hear you well.
Okay.
And the last group of presenters, probably Vladislav Tishin or somebody else. Somebody from the third presentation. Okay, not yet, but we will hope that this person will come. So we have the time from now to 12:15, so a little bit more than 1 hour. So let's aim at 20 minutes for each participant, including the presentation and the questions. Let's try to make our presentations last for about 10, well, maximum 15 minutes, and then we have small Q&A sessions. So Evgeniia, the floor is yours.
Okay, thank you. Good morning, everyone. I hope you are doing well this morning. I'm Evgeniia Shchepina, and I want to present you our paper, Multimodal Space of Users' Interests and Preferences in Social Networks. Firstly, I want to say that social networks users leave numerous digital footprints in the cyberspace, and a part of these digital footprints can be represented as some topology. For example, topology of subscriptions, music subscription, group subscriptions, friends lists, etc. And in this paper, we combine our clustering results obtained for different modalities into one single multimodal space of interests and preferences. And this paper aims to build a model of users' interests in the multimodal space and obtain a comprehensive conclusion about users' interests. In our paper, we consider only two modalities. It's music and groups, but proposed approach can be used in many variations and modalities. So it's kind of a common model and approach to analyzing social networks. And some objectives of our research you can see on the slide. The method of our research to analyze users' interests is the following. The approach is to cluster two different modalities, which are music subscriptions and group subscriptions, as I said earlier. This is called as intramodal clustering in this picture, and then combine the result into the single multimodal space of interests and preferences and cluster result graph. This is the multimodal clustering in this picture. Building a model of users' interests in the multimodal space is done as follows. At the first step, data containing the information about each modality is processed separately, and number of modality can be any. For our research is the two numbers. For each of them, we collect open data from social network Contactia. Then this data was processed. The entities are selected by corresponding threshold in some graph structure. And then these graphs were clustering. Then found communities in each graph will be connected in the one multimodal single space and also clustering. On the basis of the obtained communities, the probability of being assigned to any cluster I in any modalities is calculated for every user G according to the following formula, which you can see on the slide. And the vertices of this graph are found intramodal clustering from the first step. And the edges is the connections between these communities. Those weights reflect the probabilities of assigning users to both vertices. And as I said before, this graph is clustered, and the communities of interest in a single multimodal space are obtained. In this paper, we used the data set collected by themselves from the social network UK. It's a Russian online social media and social networking service, which allows users to message each other, create and join some groups, listen to music, playing games, watch videos, etc. Group subscriptions in our research from the user means that he or she joins the group, and the music subscription means that the user adds some audio to his or her playlist. The statistics of the collected data you can see on the slide. All the data has been anonymized because we didn't use any names and other personal information. We need just to make connections between them. After collecting data, we made some processing on it. First, we select some groups by threshold. We did this because, for example, for one group can be in the subscriptions only for 1 or 2 users, and it's kind of outliers, and the graph was a bit messy with this data. After group processing, we did the complex processing of music data. This was some issues at this step because the part of music artists are written incorrectly, so we did some NLP preprocessing, escaped some symbols, etc. Also used threshold as for group subscriptions, and used the sequence matcher to understand which different artists are the same. This is did because earlier in VK, every user can add some music and rename it, so the data has a lot of trash in it. In our research, 2 social network graph clustering algorithms are applied. The first one is the Luban algorithm, which is based on optimizing the quality function, for example, modularity score. And it works in 2 phases. The first phase is local moving of nodes, and the second one is grouping them together. So in the first phase, nodes are moving into some communities in such a way that makes the biggest increase of our quality metrics. And the second phase in aggregation of the network using the obtained to the first step community. Then each community, step by step, became only one node in a new network, and the process repeats. But this algorithm has the main disadvantage, and this is that this algorithm has the poor result with badly connected communities. And in our research, we had them. So this problem is solved by the second algorithm, the Leiden, which are based on the Luban algorithm. And these 2 algorithms are specially used for social network graph analysis. But in the last multimodal step, we use the 2 simple algorithms, K-means and agglomerative clustering, is the part of hierarchical algorithms. Because this graph was pre-processing after the other graph clustering, so it's no need to use special social network graph analysis. And the result, multimodal graph, became an undirected weighted graph with 20 vertices and 360 edges. Also, at each step of clustering, we calculate some metrics, and you can see the results on the table, on the first table. And the community size of the 3 types of clustering was not the same. So for music is from 125 to 200, for almost 300, and for groups is from 150 to almost 200. And at this slide, you can see the visualization of the community detection graphs. So the first picture with a label is the community detection for graph building from the groups. From the B picture is for the music subscriptions, and the C, the most interesting, is for multimodal analysis. With the black circle, you can see these communities is music communities, and other it's the group communities. And the more descriptive information you can see on the next slides about these communities. But here you can see that some science communities are connected with each other. It's the gray color. Also, some cinema and books clusters are connected to each other. It's in orange color, etc. To validate this model, we perform the following experiment. We select 100 random pairs from the sample of users, such that 50 lie at the minimum of Euclidean distance and other 50 at the maximum. The result in the sample is marked by experts as follows. Each expert is asked to familiarize himself with the personal pages of 2 users, the personal pages in UK. See on the general information, posts, music, subscriptions, data, and the results in Makarov was used to validate this model. And to build the alternative model, we use the LDA analysis of posts of these users, just to build an LDA model with 10 topics. The number of topics was calculated by quality metrics, and got the result that model on multimodal analysis of interest shows better accuracy, precision, and other metrics. As a part of our research, we tried to visualize somehow our results. Since our data is multi-dimensional in nature, we built a visualization based on the convolution TSNE algorithm, and you can see the results on figure 4. Here you can see that other clusters are well separated from each other. And in addition, for all users, we have been determining the average probabilities of assignment to each community and show it in the figure 5. For the users of each community, the probability of being assigned to this community is the highest. It's a quite obvious thing, and the probability of being assigned to other communities ranges from 0.1 to 0.3. And using this type of diagrams, we can analyze also volume intersection between communities and the maximum value for other communities. And as a conclusion, I want to say that in our research, we have built the model of multimodal embeddings of the user description in the space of his or her interests and preferences. And by analyzing detected communities at each step of clustering similar interests, we're assigning to similar communities. Also, all music and groups communities have a high quality interpretation, and only part of communities in final clustering have quality interpretation, because some of the clusters have like music, rock, and from group description, books, and how connect rock and book with each other, it's kind of non-trivial thing. And the scientific novelty in the proposed method is the building of this multimodal model and gives some conclusion about their interests. And as I said at the beginning of my presentation, that this approach can be used with any other modalities, not only music and groups, and can be did some more detailed analysis of some social network, cyberspace, or community. Thank you for your attention.
Thank you very much, Evgeniia, and the floor is open for questions and comments. Okay, if there are no comments or questions from the present participants, I have got a couple of questions. Can you return to the slide that is called something like clustering results?
Mm-hmm.
Yeah, so I have a more conceptual question and a more technical question. So your novelty and your goal, as you claim, is to offer a new algorithm that would be somehow better than the others. So we have several algorithms here listed, and all of them are standard, so far as I know. So could you please explain which one of yours, and how it works?
Thank you for the question. We propose not the algorithms, but the approach to combine other clustering graphs to the next level graph, as we call it, multimodal. And yes, the algorithms are quite usual, especially Kamins and agglomerative clustering. But our novelty is in our approach. We can't see this approach in the earlier papers.
So you have not described this approach in this paper and in this presentation, have you? Or have I missed the description of this approach?
The approach is here.
Mm-hmm.
So we have other modalities for our research in music and group. Then we built on these modalities graphs, which in this graph node is music artist or some group in social network. Then we connected it using the summarized number of users which has this music E and music G in our music.
Sorry for interrupting. How do you pass from different modalities to this single graph? What do you do? Do you do a projection of modalities into unimodal space, or what is the approach here?
We cluster the graph, and the clusters are the nodes in the next step.
Oh, I've got it. So all the clusters are collapsed independent into one graph independently from the modality they have been taken. So you basically project multimodal data into unimodal graph.
Yes.
Where all the clusters are the nodes of the same type, right?
Yes, for this research, they are the same.
Okay, very good. Then I ask a more technical question. Could you return to the slide with the results? So you have skipped it. Yeah. So first of all, I'm aware of modularity and silhouette as measures. There is actually a bunch of questions that also come from some of your reviewers, but also from myself. So modularity and silhouette tell us something about how coherent and how well separated the clusters are. I don't know the measures of Kalinsky, Harabatz, and Davis-Baldwin, so probably you could explain it. But one of my major concerns is what you're doing next. Somehow, in addition to this modularity, silhouette, and other stuff, you compare your clustering to LDA solution as a sort of ground truth, which is very puzzling because this is not ground truth. This is just another solution, first of all. And second, LDA is so unstable and so subjective that the way you are running it and the number of runs you use will affect dramatically your results. So first of all, your result depends on the number of clusters that you choose and other parameters. And second, even if you have the same parameters, you run the same model several times, it yields you dramatically different results. And then you are comparing your solution to that. If you compare it once again, you will get a very absolutely different whatever metric, F measure or anything. And so one of your reviews writes that F measure shouldn't be used at all for clustering, and he proposes some different metrics which are called ARI and MMI. So I wonder if you could make some comments on that bunch of questions.
We at the model evaluation step, we made some sorry, we didn't think about it when we did this research. So firstly, we just want to try this and make some results.
Okay, so what do you mean when you are writing that the performance of your model increased by 12% compared to what?
Compared to other LDA model.
But your LDA model is a benchmark, right? So okay, so you should compare then you should calculate the quality of LDA model then. For example, calculate modularity for LDA and then calculate modularity for your model or silhouette, whatever. And then say, okay, our silhouette is 12% better. But I doubt that you can calculate either modularity or silhouette for a LDA solution because it's not a proper clustering. It doesn't give you clusters, to give you distributions of probabilities.
Yes, but in the evaluation step, we think of is two users similar or not, and we calculated using vectors. So in LDA it's vectors, but in the other one, our model is from the experts.
Okay, so human evaluation. Okay, good. Yana is asking you to show the slide with the data. I'm not sure which one it is. Slide with the data. Okay. Okay, very good. I think we have exhausted our time for the first presentation. And I think I see the third presenter who has also joined us. That's very good. So thank you very much, Evgeniia, once again. And I'm passing the word to Olga Gerasimova and her paper on research papers recommendation.
Yes, hello everyone. I'll start. Okay. Do you see my presentation? Hello?
Yes.
Do you hear me? Do you see my presentation?
Yes, I can hear you and I see your presentation. Do you hear me?
Yes, okay, I'll start. Hello, everyone. My name is Olga Gerasimova, and I'm from Higher School of Economics from Faculty of Computer Science. And today I would like to tell you a few words about our work on research papers recommendation. And the motivation of our work is based on usual needs when it's necessary to search for relevant early articles at the beginning of any research, and we decided to formulate this task as a recommendation of research papers based on citation network data. Having a collection of full text articles and information about the citation links, we aim to compare the performance of text-based methods and network embedding techniques, including fusion models via text-attributed network embeddings. So as for dataset which we used, we considered an unsolved network corpus. Nowadays, this database contains more than 20,000 papers on computational linguistic and natural language processing. However, in open access, there is a collection only for 2014 year. And okay, what data we use from this database? We use articles metadata, which is presented as a single text document, and we parse it to extract necessary attributes, in particular abstracts, and then we left only alphabetical symbols. Also, we removed articles without abstracts because our goal was to compare text-based method, including attributed network techniques and just pure vectorization methods. So as a result, we obtain a citation network which contains more than 13,000 articles connected by about 68,000 station links. And so the final version of a station graph is illustrated on the slide, and the greatest connected component of this graph contains about 93% of nodes, so it's quite connected. Okay, a few words about maybe task formulation. A citation network is presented as a graph, and where nodes correspond to the research papers and directed edges of the graph indicate citation links between papers. Link prediction is formulated as binary classification on graph edges, where the label 1 corresponds to the existing nodes and the label 0 corresponds to the absence of the link. The binary classification model requires both positive and negative samples for training, and in case of directed task, the negative samples for our task consist of all inverse positive edges and the same number of randomly chosen pair of not connected nodes. That is, so the size of negative samples in our case is twice the size of positive samples. So then we decided to consider static task on the citation network in terms of predicting missing links. That is why train and test splitting was not based on time modality as for temporal task, just in terms of the number of links. And we consider several options for splitting that are written on the slide. Okay. In all experiments, we report the quality metrics average over 5 random seats for a train, and we used a random forest classifier for our classification task because based on some previous similar researches and some experience for this task, it shows best result in comparison with logistic regression, SVM, or gradient boosting. So we received features for nodes in 2 ways. First of all, we received a vector representation based on text to vectorize text attributes. So using well-known models from the left column, maybe a few words about fast text variants. They will obtain based on pre-trained on pre-trained fast text words embeddings with dimension equal to 300, and then this word embedding, fast text word embeddings, were aggregated with equal weights for the mean fast text and weighting according to TF-IDF value for corresponding to each terms in the text for weighting variance. Also, there is a typo on the slide. For word to vec, we considered dimensions 64 and 300, not 30. Okay. Second approach, which we considered when we consider network embeddings using standard node-to-vec and hop models, and also several fusion models such as graph convolutional network and text attributed deep walk models or attributed biased random walk models, which combine text information, text attributes, and information about network structure. Okay, I'll move to the results. Okay, during the first experiments, we compare the performance of structural network embeddings. We can see that undirected node-to-vec shows the worst performance. Directed variance is a little bit better, but the best result is for Hope model, which preserves higher order proximity. Okay, next experiments are related to text-based model, and it is interesting that quite simple models such as bag of words and TF-IDF showed quite good performance for different splitting. However, the best result was shown, but non-pre-trained word-to-vec with dimension equal to 300. Also, we can see that all pre-trained model degrades quality. Maybe it is due to the fact that the corpus has a specific domain oriented to the natural language processing vocabulary. And also we can see that fast text aggregations options doesn't work well. Okay, also additionally, we decided to consider a text similarity approach when abstracts, our text attributes, are considered as a vector, and we compare the vectors using cosine similarity metric and cosine similarity measure. And this similarity measure can be viewed as a probability that two papers are related to each other, and one of them could be recommended as a relevant paper for another one. So for this approach, the similarity measure threshold had to be determined, and for each embedding type, these thresholds were chosen independently. We are maximizing accuracy on the train set. So also, I didn't say that this all tables contain results in terms of accuracy, and for splitting 70 and 70% for train and 30% for text for test set. Okay, and for these experiments, maybe the main idea is that text information alone works was then, for example, structural embedding hope with the random forest classifier. Okay, and the main part of our research when we test fusion models and combine different text embeddings and fusion models. So, and as a result, we can see that graph convolution network model shows the best quality, while the other two models appeared not to be robust to different text embedding. And the best combination is word-to-vec, and this simple GCN model, and this combination allows to efficiently fuse graph and text context for our link prediction problem. And by the way, the main idea of this research was to find such combinations of maybe simple, faster text embedding and a model which can aggregate network structure. And for this approach, it is Word2Vec and GCN model. So, in conclusion, I just want to repeat that we made, I think, quite maybe a lot comparison of different in terms of yes, of different approaches as based on only graph information, only text information, and fusion models. And finally, we find the best combination of a model which enrich feature representation, achieving the best results in our task. And this conclusion are robust across different train test splits. And as for future studies, we are interested in research related to dynamic citation network. And of course, it is logically to consider time-dependent structure when we have to make train test split in terms of time modality. Okay, thank you for your attention.
Thank you very much, Olga, for your most interesting presentation. And the floor is open for questions and comments. Okay, we just have a couple of minutes. While people are thinking, may I ask one clarification question? What is inverse positive edge in the context of a citation network?
Okay. As we have a directed graph, so for example, there is an edge from the first node to the second node, then inverse positive edge is it is edge from second node to the first node. And in terms of citation, if there is an edge in one direction, that's there is no edge in opposite direction. And that is why we add all opposite inverse edges to the negative samples to learn that such that such edges
yeah, that's interesting. Intuitively, I would think that a negative example is the absence of an edge, not the opposite edge.
Yes,
but I'm not an expert in this field.
It just we want to highlight that the task is directed, and we want to learn that opposite links are bad options for citation. They will not able to exist because it is necessary that only exist an arrow and edge in one direction.
Okay. Yeah, it may be a stupid question. So your observation is an edge, or a positive edge or an inverse positive edge, and that's what you're trying to classify. So predict, like make a classification that predicts either the presence of what you want to find or the absence of what you want to find. So how come that the edge has text attributes? So a node may have.
So I just forgot to ask how we received and age representations. We have models for receiving node representations based on text or network structure, and then we use concatenations of vector nodes vector representations for considered age, and in such matter we received a vector representation for age, and this vector will be considered as features for age.
Okay. Well, thank you very much. I'm afraid we don't have more time for this presentation, and we still have a third presentation in our program.
Okay. Thank you very much.
So, yeah, thank you very much, Olga. And the third presentation is about citation network applications in scientific co-authorship recommender system. And Artyom Sosedka is present, right?
Yes, yes.
Okay, very, very good. The floor is yours then.
Today I would love to present the paper that we made for AIST. It is citation network applications in a scientific co-authorship recommender system. I'm Artyom Sosedka. I am a student at the National University of Science and Technology and researcher at SBI. I'm the speaker, and I believe my colleagues will come here in a second. Let me give you a short overview of this work. The main domain of this work is scientific communities, and we are eager to solve the problem of collaboration recommendations for others. They want to find co-authors with whom to collaborate. It is not a trivial task taken into the account the complex structure and interconnectedness of collaboration network. And there is also a complementary citation network that we can get from the domain. It is a network of papers and citations. There have been a lot of various methods and techniques in the past to solve the given task. But nowadays, we have graph neural networks at our disposal. And with this, our task stated in the graph terminology is to predict a link between two authors and to see whether or not they will collaborate. Another focal point is the inductive approach, thanks to the methods that were used in GraphSage. Let's talk a bit more in depth about the problem at hand. Our current problem is that we want to forecast potential collaborations in the scientific communities and the network, which is knows the fate due to various reasons stated beforehand, one of which is the innate complexity of the co-authorship network. And in this paper, we proposed that aggregation of complementary citation network could significantly improve the efficiency of predictions due to capturing latent connections not seen in the original graph, especially on the edges of original graph. In the paper, we studied our approach on the high-energy physics dataset, particularly because it has two networks we're looking for. It has citation network, and for once, it is outdated. Unfortunately, data has been collected only from 1993 to 2003, and it has little relevance to the nowadays, and we can't predict accurately for authors that are included in this dataset. Sure, that could be able to determine whether articles written by the author or not. And to combat this problem, we made additional preprocessing to restore connections. We passed metadata from the internet, from articles and authors, and mapped them together. Our current method consists of two models. The first model generates a vector representation of the publications in citation graph using unsupervised graph stage. It aggregates information about the set of neighbor nodes in order to produce embedding of the target node. And additional node features are being extracted from abstracts via fast text. Those representations then are concatenated with research interest matrix, which is one hot encoded vector representation of research interest of authors. And after this, the next model, which is a link prediction model, uses its information on collaboration graph, where graph stage, and constructs potential links applying a binary operator to the pair of node embeddings, such as L1, L2, hard mode. We used average and inner product, but about the results, I'm going to talk about a bit later. Those pairs then passed through the dense classification layer to obtain probabilities of those links' existence in the network. Here you can see the pipeline in more detail. As you can see, we've used the fast text with dimension of 20, graph stage on the citation graph with two layers on with dimension 128, which is then aggregated via sum, concatenated with research interests, and then passed onto graph stage with collaboration graph, which is then passed through dense classification layer. We want to talk about several interrupts which we considered for this method. The first one is I'm going to talk about unsupervised methods that we wanted to use for feature extraction on networks. Those methods are node to vec and add tree to vec, but unfortunately they lacked in performance compared to graph sage, and in the end we use graph sage for feature extraction. We also really wanted to use BERT as our text feature extraction on abstracts that we used in citation network, but unfortunately we lacked time and we weren't able to finish the paper if we were to use BERT. It is in our plans in the future to use BERT when we won't have such harsh restrictions on time and power. Here are some results. The first two are results from the different model. So we constructed two different approaches. The first one is the classical one. We do not have any connections between two networks. The first network is article citation network, and the other is collaboration co-authorship. And as you can see, they do not have any of the best results. The first method is not using any article features, and the second one is using only abstract features for nodes. The last three methods which we used for our proposed method, it has graph sage with mean aggregation in articles, in citation network, and graph sage with mean and max pool in the last case on the collaboration network. As you can see, we have three different models which excel in three different types of accuracy metrics for accuracy, for ACROC, and for F1 score. We also use different link prediction operators, those binary operations used in second graph stage. And we have found that Hadamard, L2, and L1 shows the best results overall. In conclusion, I want to say that our approach, our naive approach of aggregation of complementary networks actually works, and it performs better than our constructed model, which we used in the results for the first two. It shows considerable increase in performance on several metrics, and we would love to continue our work in this field to find better result, to find better approaches, to find better results on the two graphs, two complementary graphs. I would love to thank you for listening, and I am open for questions. I would start our work. Thank you.
Thank you very much, Artyom. And I would like to encourage the audience to ask some questions. It's not good if only the chair is asking questions. Please, come on. Yeah, I would only, I'm not an expert in this field. I can only repeat one of the questions of one of the reviewers about the depth of aggregation. If it's missing, could you comment on that? Or probably you don't agree with this comment, that it is necessary to have this information.
Can you please repeat the question, because it's very hard to hear this.
So the most interesting part on the depth of aggregation for co-authorship and citation network is missing. That's what the reviewer says.
Yes, I believe I understand what you're talking about. It's about reviewer. We were not really considering this as, but as the important missing information. But as reviewer stated, we are going to look into it in our future work. We are currently exploring quantitative and qualitative approaches to improve, and maybe we are going to consider what the reviewer said. We're not really sure that it is the essential part that we're missing.
Okay, thank you very much. Thanks everybody for coming, and thank you, Artyom, for your presentation. And I believe that our session is over and we can go for a break.
Hello, everyone. Welcome back to the second day of the conference. And today, after the NLP roundtable, we are moving on with the invited talk. And it is my great pleasure to introduce Jeremy Barnes. We worked together for several years in the language technology group at the University of Oslo, and then a very sad thing happened. Jeremy left us to become an assistant professor at the University of Basque Country, where he's now. We are, well, not we, I guess. Jeremy is organizing some of our shared task on structured, like fine-grained sentiment analysis next year with my humble help. And today's talk, I guess, will touch this topic quite a lot, but maybe many other aspects as well. And yeah, I guess we have how much time, Kira? An hour and a half, but yeah, I really hope that we will have plenty of time for questions and discussions. And I really hope that this talk will be interesting, not just for NLP people, but also for those from other tracks of the conference. Since, as we discussed half an hour ago, like one of the strong points of this conference is its multimodal and interdisciplinary character, right? So I do hope that Jeremy's talk will be of great interest to all of you and to all those who are joining us in Zoom. Okay, without further ado, the floor is yours, Jeremy.
Thank you. Okay, thanks a lot for having me here. Like Andrei said, I'm going to be presenting this. I just started as an assistant professor at the University of Basque Country, and I'll tell you a little bit about myself and how that relates to this talk now. So the first thing, motivation. Why did I choose this title? This has a little bit to do with me and a little bit with the state of things in NLP these days. So for me, when I started my, let's say, NLP research career, I started working on emotion analysis and sentiment analysis. And at the time, I would say most of the data sets that I worked with were sentence classification data sets, right? This was pretty common. I think it's still quite common for a lot of data sets to be sentence classification data sets. Some examples of tasks that are done at sentence level are things like sentiment classification, which I've mentioned. It's going to be a kind of running gag. So one of the examples I'll give throughout the talk are going to be sentiment, since it's something I've worked with a lot. Other things, topic classification, language identification is often done at sentence level, and intent classification. So in chatbots, whenever you want to know, somebody asks a question, you have to decide what kind of question is it, what are they looking for? These kind of things are often done at sentence level. What I wanted to show with this is that there's a lot of tasks. It's not just something that's specific to sentiment. It's something that's relatively broad that we do when we're working with NLP. And another thing that I'd like to point out is how prevalent these sentence classification tasks are in benchmarking models. So when we have a model, we want to know how good it performs. We have a tendency to go towards these. So if you know the multitask benchmarking data set called GLUE, it was a very popular data set. It worked with a lot of sentence classification tasks. Also, there's a more recent one called the Dynamic Sentiment Analysis Benchmark, which again, it's an adversarial version. So I'll talk a little bit more about it, but it's just to show you that this one is also there. And also, whenever people start benchmarking these large language models these days, a lot of these are also done with sentence classification data sets. So it's something that happens, you find in a lot of tasks. I'm going to speculate a little bit about the reasons for this. One of the main ones is just the fact that it's easier to annotate this. So depending on the task, there's times you can semi-automatically annotate many of these things using star ratings or user ratings for sentiment analysis, or you could do it with other ways, some kind of metadata. And at the same time, if you're just actually manually annotating, it's a nice sized chunk of text to present to an annotator. So it makes things a little bit easier. And because it's easy to annotate, it has a tendency to have larger data sets associated with it. So you get large data sets, which is better for deep learning models. So it has a tendency to propagate in that way, right? And also, because the data sets are larger, you can have relatively large test sets as well, which helps whenever you need to have statistical differences between models, it's relatively easy to calculate. But conceptually also, this allows for kind of simpler train test procedures, right? You have a single sentence, a single label, and usually you have a couple of categories, but it's not too big. So for somebody getting into NLP, whenever you're just starting, it's also conceptually easy to think about how to do this, as well as being easier to batch. Whenever you're doing training on these large models, it's important to be able to do it efficiently. So it's all kind of helpful in this way. So that's maybe one of the reasons that this is so pervasive. So today, what I really want to try to convince you is that sentence classification is maybe not always an ideal way to benchmark models. Now, this is not to say that all sentence classification is maybe incorrect, but that a lot of times we have a tendency to overuse sentence classification as a proxy for model performance. And there's a lot of caveats there. So I'll talk a little bit about some of the problems with sentence level classification. Starting off, I want to talk a little bit about the values that we have whenever we're talking about these things. So as a machine learning community, I take NLP inside of this. There are certain values that have a tendency to pop up more in papers than other ones. So Birhani et al., they looked at this paper called The Values Encoded in Machine Learning Research. They took 100 of the most cited machine learning papers in the last couple of years, and they annotated them for the kind of values that the papers were pushing forward in each part. And kind of unsurprisingly, you get this kind of a thing, right? Performance, generalization, efficiency, researcher understanding, novelty, and building on previous work. This notably leaves out things like robustness, robustness to bias, and several other things. And I guess what I really want to point out is that performance here is the main metric for what values we want to have, right? If you have a good model and it performs the best, then this model is likely to get accepted, or the paper is likely to get accepted into a high-level conference, and it's likely to be cited more often. But that has problems as well, right? I mean, when we're concentrating things on accuracy, F1 or BLEU score, it's helpful in a way because it allows us to kind of fairly compare models across a lot of tasks, and you don't have to think about too much. You just think about the performance, and you're fine with it, right? You don't have to think about, I don't know, all the possible variables between the data. We just think about the one metric, and it allows us to kind of focus on a single number and be happy when the number goes up. So it gives us a kind of objective criteria for whenever models are better. So a lot of times things happen like this, where we see these things where on many benchmarks we achieved superhuman performance. So we've gone past what humans can do. And the question is always whether that's true or not. And today I'll try to convince you that maybe that's not actually true. So the case study that I'll be looking at is sentiment analysis. And here, what I've done is just given 5 of the most common sentence level classification data sets in sentiment analysis. So we have this movie reviews data set from Peng et al. 2002, a camera review data set, subjectivity data set, MPQA, and Stanford Sentiment Tree Bank. And these are all kind of sentence level binary classification. So positive, negative, basically, except for the subjectivity one, which is subjective or objective. But these are a couple of examples, but there's actually quite a few more. I mean, there's tons of data sets that are out there at sentence level. This is only in English as well. So the current state of the art on several of these data sets is incredibly high, worryingly high, actually. The Stanford Sentiment Tree Bank, for the binary one, like I said, the accuracy right now is at 97.5. For the movie reviews, 92.5, and for subjectivity, 95.5. So does that mean that these models are great, right? They should be incredibly good if they're able to do this. And we would expect them to be able to be relatively robust and things like this. I've had a lot of people actually tell me, seeing these numbers before, well, sentiment analysis is basically solved, right? Because I mean, if you're at 97.5, you're done. I mean, choose a different path, do something else, and move on. But having worked in this area for a while, I can relatively guarantee you that it's not actually as good as it looks. So yeah, not really. So me and some colleagues at the University of Oslo, we looked at, we had a paper called Sentiment Analysis is Not Solved, where we took a number of sentiment data sets, and we collected a subset of sentences that 4 models, so a bag of words, just has a kind of baseline, by AIST, Elmo, and Bert, which was state of the art at the time. And what we looked for was the errors that all of these made. So we took all of the data sets and collected a subset where all of the models failed. And then we went through and we annotated these for 18 possible categories. So it was things like, well, I'll talk about it in a second, but 18 linguistic and paralinguistic categories that could have led to the error. So things were, we had some that were annotation related, things like incorrect labels. There were a lot of incorrect labels in these, which makes you think about, if you're getting 97% on data with incorrect labels, what does that mean exactly? Right? A lot of things also that were data related. So things like non-standard spellings and emoji that the models had a lot of problems with. And set up things related, things like negation, modality, amplifiers, etc. Right? There's a lot of kind of the interesting phenomena that seem to be located inside of these errors. So what I wanted to say with that is that the sentence level setup kind of hides the fact that models perform really poorly on certain subsets of the data, right? Things like negation, things like modality, and this kind of compositional knowledge. When you work at sentence level, you can kind of avoid that. You can work with heuristics to a large degree. And whenever you just take data off the internet that has been, I mean, you kind of filter for binary classification, filtering out all the middle, all the difficult parts, then it becomes quite easy to avoid that. Right? The other thing is that a lot of these data sets that I've just mentioned before are actually simplifications. So they're not the original data. This MPQA data set that I mentioned before is actually very, very complex, the annotation. So it's annotated for direct subjective expressions, indirect subjective, things like this, as well as targets and sources and all of their relationships. And we've actually, the one that most people use is just a sentence level reduction of this to binary sentiment. So we've removed all of the complexity and just kind of set to this easier sentence level data set. Same thing happens with the Stanford Sentiment Tree Bank. This was a really interesting data set that's annotated for polarity at each node of a constituency tree. So each one was annotated separately. So what you get is this really rich, dense data set where you can look at things like compositionality. So for example, in this example we have here, the high level negation actually ends up negating all of the kind of positive polarity, right? And you see that very clearly here because it's been annotated. So you can train models on this. You can also test if your models are able to do this well, which is quite interesting. The problem is, again, the one people normally use is just the binary sentence level version. So people don't have a tendency to use this data because it's slightly more complex to work with. So yeah. And there's a lot of other sentiment data sets where this happens. Again, I mentioned sentiment because this is the area I know the best, but there's a lot of areas where this happens as well. So they've been converted to sentence classification and then further binarized. So you have to ask yourself whether that is actually something we want to keep on doing. And I guarantee you these data sets are used very often when we're benchmarking models, at least in English. It's not something that happens only in sentiment analysis. Like I said, for things like language identification, a lot of times working at sentence level doesn't make much sense. So we have a tweet from a good friend of mine. And if you know the meme, you probably know this. Hello, lange in de Buchse, my old friend. So hello, X, my old friend is a kind of meme that is constantly done through the internet, right? But here, if you're trying to predict the language of this tweet, you're going to have a problem because there's not one language. It's a mix of English and Norwegian, right? And I'm sure this happens. I mean, this happens everywhere throughout the internet with all the languages. In the end, trying to do it at sentence level maybe is just not the right level to do this at. Right? So we have to ask ourselves if that's something we really want to keep on doing as well. To move on a little bit, another problem with the sentence level setup is that error analysis is quite difficult. Knowing whenever you have a sentence level prediction, what the change, what the part of the data was that led to that prediction is very complicated. There's been some work on that. So doing things like looking at saliency maps or attention maps of the predictions and trying to use some kind of adversarial maps to see if it's really that caused it. But there's been some back and forth. So I don't think it's entirely, I'm not entirely sure that this is a perfect way of looking at this. So There was these two opposing papers, attention is not explanation, and then attention is not explanation, which kind of go back and forth on whether it's a useful way of detecting, let's say, doing error analysis on a sentence level. And from my experience, I can also say that doing error analysis at that level, it makes it very hard. You're always making kind of subjective decisions about what could be the reason that the model made an error here. Finally, and this one I think is super important, sentence level prediction is not always particularly informative. Let's look at one example at least. Let's say if we have this model we were talking about earlier, it performs binary sentiment prediction, 97.5% accuracy. So it's superhuman level, it's incredible, right? What would it mean if that model predicts positive for the following sentence? James went to the store. What could it possibly mean, right? It's a model that's been trained on either positive or negative, so it can only output positive or negative. But it's ignored the fact that not everything in the world is positive or negative. Some things are just neutral, right? James went to the store. This doesn't have any sentiment. So we have to ask ourselves sometimes, when you have a model that does super, super good on a task, is that task actually interesting or not? And I would suggest that maybe in this case, if you're getting up to these levels, it's maybe not interesting anymore. Okay. So the elephant in the room, do these large language models reduce these problems, right? I mean, we've had this explosion recently in NLP of incredibly large language models that are able to do lots of things. I won't go into all of it. I'm not going to go into tons of detail about this, but what I want to do is just kind of point out some of the models that have come up. So we have things like, obviously BERT is the most well-known, but then you have GPT-2. In this case, it's just a little bit older, so GPT-3 doesn't exist yet. But we have things like GPT-3. I mean, if we go through model size, BERT, the BERT large had 345 million parameters, which at the time was incredibly large. It was a giant jump from all other model sizes. We go to the GPT-3 and we have 175 billion. And then I think just another one I've looked at recently is this Megatron from NVIDIA, Megatron Turing, which has over 500 billion parameters. So these things are getting very big. And at the same time, the performance, at least the numbers are going up. And they're going up very fast. So the gains in performance have becoming bigger and faster as it goes through. So this is a graph from the Dynabench paper from Kiel et al. 2020. And they plot here the saturation of benchmarks over time. These benchmarks include both vision and NLP, but I think we could kind of agree that the benchmark situation is basically the same these days in both of the fields. And as you see, as time goes by from 2000 up to 2020, benchmarks last less and less time before it gets up to human or superhuman performance. So this is something that we know that the numbers are going up. We just don't know maybe what's going on behind that, right? So another important point is that inside of these benchmarking data sets that we're using, so the things we're referring to here, sentence classification is very commonly used. And of the task used, a lot of times the largest gains are reported on these sentence classification tasks. So this is something that is also very important to take into account whenever we're thinking about this. So yeah, like I said, we get the better numbers. The gains on this Stanford Sentiment Tree Bank have gone from Elmo being around 90, 91.8 to 94.9 with BERT, and then Electra Large was 97.1. And there's another one that I didn't mention, but I forgot to put here, that is 97.5. So it's gone up quite a bit, very, very fast. And again, the question is always, the other thing about these large language models that's really interesting is that they're few-shot learners. So whenever the GPT-3 paper came out, this language models are few-shot learners. The interesting thing was that with very few, they don't have to actually fine-tune the whole model, actually give it just a couple of examples, and it would do almost as well as fine-tuning state-of-the-art models. So here is as an example from this on the superglue data set, you can see that we have this kind of random guessing baseline, and then 0 shot, 1 shot, and few shot, the orange being the few shot with 32 examples. And giving it only 32 examples, it was able to get better than a BERT model that had been fine-tuned. So that was pretty amazing right there. And it turns out, obviously here it looks like the bigger the model, the better it is in this. But a couple years later, Schick and Schütze came out with a paper that showed that you don't need very large models to be able to do this either. You can do it with smaller models. So this was an example on Superglue again with 32 training examples, but using Albert and their approach. And if you look at it, gets as well or better than GPT-3, but using a model that's 3 orders of magnitude smaller. So it seems that they're really good at this few shot thing. And another example is from this Guo et al. Paper, making pre-trained language models better few shot learners. What they do is they show that there's a couple of tricks on using this prompting. Prompting is the idea that you can just give a couple of examples as input and then ask for the answer as output. And instead of having to train it, you just send it all in as input basically, and it learns from that. They showed that doing this a smart way, you can actually get really good benefits in hand. For example, with as few as 16 examples per category, you can have for example, on the Stanford Sentiment Tree Bank, around 94–95% accuracy, which is quite impressive. The question is, do these actually lead to generalization? And unfortunately, there's a growing amount of evidence that they have serious limitations. I'm going to concentrate just on one of these limitations today, and we're going to look at negation as an example. I take negation as an example basically because negation is found in all languages in the world. It's a very pervasive thing, and it's something that humans can deal with very easily, right? If I tell you that a light is on and the light is not on, you can extrapolate to what that means. It turns out that language models cannot. So there was large language models seem to fail completely actually at handling most negation. That means, well, to give you a couple examples, there's a paper by Ettinger from 2020 in Tackle that's called What Bird Is Not. And they introduce a suite of psycholinguistic data sets, one of them being negation. And it seems that the models were completely unable to deal with negation. So if you ask BERT to kind of fill in a sentence, and you say, a robin is it gives you things like bird, right? A robin is a bird, a robin is a robin, a lot of these kind of things. If you say a robin is not it gives you things like bird, a robin, etc. So it's not very good at figuring out what the difference is here. Kastner and Schütze do something very similar. They have some probes instead of the psycholinguistic tests, but they find the exact same thing for large language models. So this one, the original one was just on BERT, but then it's also been looked at in GPT-3, some other language models. So it seems like the bigger the model, it doesn't really help with this. So it's not a problem of training data necessarily or model size. Then we also have this one from Hossein et al. Who do the exact same thing, but instead of just kind of a general one, they look at the task of natural language inference. And again, found the exact same thing, that on a negated, let's say if you take the benchmarks and look at the negated subset, the models perform quite poorly at these. And finally, we debated all this beyond accuracy, which it won a best paper award for ACL 2020. They found the exact same thing but also including, let's say, available sentiment classifiers that are in industry. So it's something that happens in academia, it's something that happens in industry. It seems to be quite pervasive right now. So that's kind of problematic. If these models that are getting this great percentage, they're getting great performance, but they can't deal with this simple, basic, universal concept of language, right? So another problem is that whenever people actually report this performance on these benchmarks, a lot of times, they don't actually provide any error analysis. right? So they give us the numbers and they say the numbers are this, and that's it. And the problem is later you don't really know. So a lot of these papers that I've shown have come out years after the original models were out. So we weren't aware of these problems that the models had until much later, despite the fact that they were probably there from the very beginning. Haven't changed much. So without doing these kind of error analysis, we can't really know where models fail. So it seems like it's not just a problem. The large language models don't really solve a lot of the problems that we have with this sentence level classification. So what can we do instead of sentence classification? Let's see, I'm gonna take a drink. First, I'll give a couple of options that I think would be maybe something interesting that we could do. The first one is a evaluation and maybe a reformulation of tasks. So if you have this kind of setup where it's one label per sentence, is there some other task that's more interesting that you could do that's maybe picking out several entities and the relations between them, something that's more structured prediction? And again, going back to my kind of running example, I'll go with sentiment analysis. So like Andrei mentioned, we have been working on this task of structured sentiment recently. And just to give you an example of structured sentiment, this is given a sentence, you find all the opinion tuples, where a tuple is an opinion holder, an opinion target, an expression, and the polarity that kind of relates these. So that's basically saying, not just saying for a sentence, what is it positive or negative, saying who thinks what is positive and why, right? So it's a lot harder to do. So to give you an example, we have this one, which is some others give the new UMUC 5 stars, don't believe them. Whereas some others is the first opinion holder. We have the new UMUC, which is the target, and then 5 stars, which is the expression. And then all of this is basically saying some others thinks that it's positive about the new UMC, and they say that it's positive because it's 5 stars. So it gives it a 5-star rating, basically. And we have the second sentence, which is don't believe them. So it has the don't believe, which is this negative expression, them as the target. And here the holder is implicit. So it's implicit, we understand it's the writer, but it's not actually there. So we have some flexibility here. We've been working on this for a while. So there's quite a few data sets available now in some of the languages. The largest ones are in Norwegian now and in English for this. So we have this Nurek Fine, which we recently released in Norwegian. It has 11,000 sentences, and it's quite well. I mean, it took a while to annotate. We took our time, and we're relatively proud of it. And the MPQA is the other large one in English, which has around 10,000 sentences. For other languages like Basque and Catalan, or let's say other Western European languages, Spanish, Italian, French, or Dutch, you have kind of medium-sized data sets available. So we have data for this, and like Andrei said, we've actually started a SIMAVAL shared task on this year. So this will be the first iteration. We're thinking about maybe doing further iterations in the future. So if you're interested in participating, feel free to. But going to the advantages, what are the advantages then of this setup versus this kind of sentence level setup? Quite a few. So the first one is it's a more realistic task, right? Again, looking at this kind of sentence level, like we saw before, John went to the store saying whether it's positive or negative doesn't make too much sense really. Whereas in this task, we could easily just have that as no prediction, and that would be a valid prediction here. Second one, it has more informative predictions. So if we actually get models that are able to do, let's say, this superhuman level of performance like we have on the binary one, the predictions actually be useful then, right? If you're able to tell who was thinking what about what, then it's a more interesting downstream task in that way. Secondly, it's also easy to perform an error analysis because you have all of the parts. So I've actually, for the shared task, I've actually set up some automatic error analysis scripts that will be running on all of the participants. So it's something that you can do a little bit easier than at, let's say, sentence level. And finally, it's also super hard to do well with simple heuristics. You can't get 50% with a simple baseline, right? You're going to get very poor coverage. You're going to get very poor things. So you have to actually be doing what you think you're doing to get good results for this task. It's not to say everything's advantages. It also has some disadvantages. The main ones being it's harder to annotate well. So this is not something you can do with crowdsources. We worked with trained annotators, and it took several iterations to be able to do it well. And even so, there's always some more difficult parts with that, right? So you have to look a little bit and decide how much is it worth it. And also, obviously, at the same time, because it's to do this, it's also more expensive. So you get less data for the same amount of money, basically. But I would argue that it's also more interesting data in the end. And also, I'll talk maybe a little bit about some ways to mitigate this problem at the very end. So option 2, instead of, if we don't want to reformulate, we can also create some challenging data sets. So if you're going to do something at sentence level and you want to do it, make sure that it's at least a challenging, difficult problem. And there's a lot of ways that we can do this, luckily. So one thing is to use linguistics. So the paper we said earlier, this What Bird Is Not, took a whole suite, a lot of tests that were available from linguistics, from linguistic annotated data, specifically psycholinguistics, and tried the models on these. So linguists, luckily, have been working for years on trying to figure out what parts of language should be easy and hard to do. And there's a lot of data out there that I think could probably be interesting to pull in here. And that would be great for NLP. So to give you one example, I think I already gave the example earlier, but this is an example from the paper, whereas we have a robin is a bird robin, and robin is not a robin bird. As you look for both of these, the predictions are basically the same. So that was the interesting thing from the negation one. But there's actually quite a few tests there, so it's not just negation. The other thing we can do is create challenging data sets using domain knowledge. So this paper I mentioned by Ribeiro et al., this Beyond Accuracy checklist, they introduce a suite basically that lets you program tests semi-automatically. So you can do things like do some sanity checks that your model is able to do well on some basic things. And you can also check that it's robust to certain kinds of noise. So the example they gave in the paper again was sentiment analysis, and we have this example of a template where it's I, negation, positive verb, the thing, right? So very short sentence, but the good thing is you can then have lists of negations, lists of positive verbs, and lists of things, and just double check automatically whether the model is able to do these things. It turns out, unfortunately, that the failure rate on these very simple things was 76%. So the models were failing on these very, very simple negations. At the same time, we also have this testing NER, so making sure that it's invariant to certain kinds of small changes. If you change, for example, a named entity in a tweet, like, thank you, we got on different flights to Chicago. If you change Chicago to Dallas, that shouldn't have a big effect on the output, but it turns out it does sometimes. So they introduced this software that basically makes it really easy to check this stuff really quickly, right? And it's not just for sentiment analysis, it's for lots of things, but it's a great idea to have something like this as well. Third, you can also use error analysis techniques to create challenging data sets. This is like the one that I mentioned before that I worked on with sentiment analysis is not solved. So here, what you have is the idea that on your test set, actually, you have some kind of annotations that tell you what kind of phenomena are there. And then you can compare models across these different subsets of phenomena, right? So here you would have something like a reasonable model. It does okay at sarcasm the best, but better model does better on modals. And an even better model gets negation and then emoji and spelling the best, right? So you have a bit more of a behavioral explanation of what your model is doing, not just the primary number. And finally, you can also create challenging data sets using adversarial examples. So this Dynabench that I talked about earlier from Kiel et al., the idea is to have a model in the loop, so a strong model, and for humans to create examples that fool the model. So for here example, we have this, again with sentiment, but it's you try to find examples that fool the model, And if it fools the model, then they automatically add it to the benchmark. If it doesn't fool the model, it gets filtered out, basically. The hard part about this is doing it well to where you create a realistic kind of data set, because it's very easy to kind of fall into, let's say, simple ways of fooling models. But if you set it up well, it's a great way of creating benchmarks that concentrate on the difficult aspects of sentence classification. And finally, the last option that I'll give you today is to change the annotation paradigm a little bit. So we've been talking about how these large language models are few-shot learners, and it seems like we're going to use these more often. And the great part about that is if they are learners, we can kind of change paradigms. So normally what we've done in the past is we've had a very large train set, right? Around 70, 80% of our data, small dev set, and a small test set. What we can do now then is kind of flip that around a bit and have a small train set, a larger dev set, and a really large test set. And why is that interesting? Mainly because you could do two things. Before, the difficult phenomenon that we had in the data, we're normally concentrated a bit more in the train set just because of the size, right? But now if what we're doing is we don't have to worry about using as many examples, if we have models that can learn from fewer examples, then we can really concentrate on making larger test sets and make sure that the test set actually covers all the phenomenon, the difficult phenomenon that we want, right? And we can concentrate on that a lot more than making, let's say, incredibly large train sets. This also means that when we're making these decisions on annotation, we can actually prioritize test sets a little bit more, and with, let's say, less data, probably still have a really good, interesting benchmark for modern language models. Okay, so I'll conclude really quick. First, use sentence classification with caution, right? The performance really might not correlate well with downstream performance on other tasks. So be more than anything else. This is especially for people who are, I think people who are new to the NLP community, who just come in, probably are not aware of these difficulties as well. Second, use the data sets as originally intended when possible. So try to avoid these simplifications that I mentioned before for the Stanford Sentiment Tree Bank or the MPQA. If possible, try to use the original data, because I mean, people put a lot of effort into that, but whenever you simplify it, people don't put as much effort, or they don't look through the data as well a second time. If you still really want to do sentence classification, I would suggest a couple of things. First, consider these additional kinds of evaluation that I mentioned. So this checklist that I said earlier, Dynabench, or one of the many challenge data sets that have appeared recently for a lot of tasks. I would also say that for right now, a lot of these things are very much centered on English. So I think we need to start moving them quickly into other languages. As a community, we have moved into multilingualism relatively quickly, but it's something we still need to push really, really hard on. And also don't report just performance, right? With all of the available data that I've just mentioned, the software, an analysis of model performance and failure behavior is really a lot easier than it used to be. Okay. Second, if you're conducting an annotation project, like I said, I would consider annotating a more complex, realistic version of the task, if possible. Also try to include some other metadata that'll enable testing model behavior later. So if you have things like, if you're able to search for things like negation, these kind of things, to know whether that's available in the test data, it'd be super helpful for looking at later. And it's, whenever you're annotating is obviously the best time to do this. If you have to go back through later, it's a lot harder. So take the extra 5 minutes and add that in as metadata into the annotation. Next, concentrate a little bit on adversarial curation if possible. So trying to concentrate on these very difficult things that you know models aren't good at it. And also consider concentrating more on creating representative dev test sets than just really, really large training sets these days, maybe. So returning to the original question, is it time to move beyond sentence classification? As always, we're not going to give a simple answer. I would say it depends a lot on your task. But for things like sentiment analysis, emotion analysis, these kind of things, I would suggest that there we can move on, at least, minimally. Also, like I said, the data sets are often annotated for a different purpose. And we have models these days, models and data sets, to be able to do the full task now. So the baselines that we have for this structured sentiment data set, or the structured sentiment shared task, can run on your laptop, and they can be done in a couple of hours. So it's not something that you need necessarily tons of compute for to be able to get a baseline. Whereas before it was maybe a little bit more difficult. All right, so we can do it. Let's do it then. And that's all. Okay, thanks for your time.
All right, I guess we still have at least half an hour for questions. And I guess we'll do it this way. So you just raise your hand. I'm giving you the mic and turning the camera. Yeah, I will just turn the camera. I guess it will be easier. So that, yeah, here you are. Here you are.
I'll try not to spend the half an hour we have. Oh, thank you so much for your talk. Like I reciprocated all the points you've made, like completely, and like there are lots of things to talk about actually. Like, you know, together with my colleague Maria Tikhanova, we've spent like last year doing the aftermath of the glue methodology. You know, there are a lot of problems with benchmarks, and some of them like they lead to the things like that. And I myself, like I was, I fell into this consideration that analysis is just basically solved until somewhere like in spring, I got this Hugging Face summary, and someone wrote like, why are state-of-the-art models so bad at sentiment analysis? And there were like basic examples that were absolutely obvious for people like to consider whether it's negative or positive, and like the state-of-the-art models from the superglue benchmark, they just completely messed it up. So the first question I'd like to discuss is like, you know, in your paper that sentiment analysis is not solved basically. Did you measure, you know, the human benchmark on these complex tasks that are, you know, difficult for the models themselves? So are these examples that you have filtered out, are they actually like difficult for humans too, or are they obvious?
Yeah, thanks for your question. So we didn't actually do any inter-annotator agreement or something like this to check for it. But from my experience, I could tell you that most of them were relatively straightforward. There's some examples, there's some kinds of phenomena that are quite difficult. So things that require world knowledge to understand. A lot of times, for example, proximity to something that's nice could be a little bit more difficult for a model to see, or I don't know, star ratings, if they're different from one place to another, that could be a little bit complicated. Knowing whether, let's say, for a certain domain, if it goes to 5 stars, if it's a 5-star rating, it's good. But if it goes to 10 stars, that could be kind of bad, right? These kind of things, I think, are probably not easy for humans either. But at the same time, no, we didn't actually look into what the human baseline would be.
Thank you. So we've got like very similar results, but for the natural language inference task this year, actually. So, you know, in the glue benchmarks, there is the diagnostic data set, which is like the most rich annotated with linguistic features. And what we did, actually, we have augmented this data set with the same format and have, you know, we had all the annotation from that format like preserved. And we have basically translated it into 5 European languages, experimented with the multilingual models. And what we got is like quite the same, like negation completely messes everything up. But other features like that are not expressed lexically in any way, some kind of complex syntactic features or semantic features, they also mess the models up. So they're also the problem while they are presented in the data. So they are not learned while fine-tuning procedure, you know. So like maybe we should, you know, reconsider our fine-tuning processes. And what actually was quite interesting, that adding more data to fine-tuning kind of helped. So some of the features that are at least expressed lexically, like some simple syntactic features, and some of negation processing was like better from epoch to epoch if we add more data. But if we don't have enough data, then we're doomed actually, and we cannot generalize over such data sets like diagnostics. Yeah. So how would you like put this into the context of other tasks? Have you maybe like, you know, dived into the results that that are like given from the other tasks, not just sentiment analysis? Yeah.
Yeah, thanks. So other tasks, I mean, I haven't gone as far into for the sentence level kind of stuff, no. One thing I can say is for negation, this is something I've been working on for a while. So we have a couple of papers also on trying to get sentiment classifiers to do better with negation using multitask and transfer learning and things like this. And we get a little bit better, but honestly, right now, it doesn't seem like they want to learn negation. So I think there's a couple of things. One thing is when you're dealing with things at sentence level, to get a dense enough sample of the phenomena that you're looking at, and to make sure that that's the one thing in that example that changes the prediction, it's quite hard. So you really need tons and tons of data at sentence level to be able to pull this out. So I think that maybe if we kind of stop looking at things at sentence level exactly, we're looking at smaller sections, it might be a little bit easier to augment these things automatically, rather than trying to just kind of, you know, throw more and more data at the models and see if that's going to help. But at the same time, I'm not exactly sure about the best way of augmenting these things automatically. Like I said, I've tried with multitask learning and transfer learning and had, let's say, so we had a couple of papers. What we tried to do is we have some negation scope data sets available. And the idea was to either use that directly through transfer learning or multitask learning to, at the same time, have a single model that kind of learns from both things. So from the sentiment data set and also from the negation data set. And we had mixed results, let's say. So it seems like, I mean, we have one paper where it worked quite well, and then some follow-up papers where it has not worked. So I'm a bit skeptical about how good just doing that will be. Until we find a slightly smarter way of augmenting this.
That's the last one, I promised. Okay, yeah. I'm really happy that maybe this year we got like a few projects that address this problem. Like we have adversarial glue, by now we have robustness gym. Well, they basically do this thing. So they have the correlation analysis of what factors impact the model performance, like the length of examples, the other linguistic features, and so on. So basically, I had the kind of hypothesis. I don't stand by it lately, but maybe that's kind of interesting idea that while we have our models developing and the state-of-the-art numbers are increasing, then still we should just change the form of the task and it will still be complex and difficult enough for our models. For example, if we have a binary classification on sentences or text, that's like the simplest form, but then we can move on to, sequence classification to show where are the features that are important. And maybe then after figuring out the features, we can move on to like sequence to sequence and implement the knowledge that we got. Maybe we should like move on to sequence with sentiment. I don't know.
Yeah, no, I agree completely. I think that's I think it's the kind of path that we should be taking now is pushing towards these slightly more complex tasks. We've gotten, like you said, on the basic tasks, we're doing good. We've gotten to that point to maybe it's not really interesting to keep on doing that. So yeah, I agree completely. Move on to sequence to sequence or sequence labeling, some kind of structured prediction in a way, right? Yeah. Thank you.
Any other questions? Yeah, I saw a hand there.
Actually, I have also two questions. The first one is don't simplify the task. Can you explain simplifying times? For example, have sentiment analysis. What do you mean?
So I'll go back to the slide that I had. Let's see, the first one here. Right here. So for example, the MPQA dataset is annotated something kind of like this, quite similar. What they did is just to create the binary one, you would just kind of go through and say, are there more positive than negative in this sentence? Then it's a positive sentence. Are there more negative than positive? Then it's negative. Is it exactly the same? We remove it. That's it.
Another thing that a little bit from another background, actually we do uncertainty estimation more of computer vision on everything, and I have the question about this, because some of the example you show that, for example, an annotator can say that I don't have an idea how to correctly identify this and everything, but for model you're forced to say it's either this or that, and it's basically don't have this option. So how do you think how relevant is this addition for the model to like estimate that its own error or like on uncertainties for the NLP?
Yeah, great question, actually. So this has actually been a topic that's becoming more and more popular. There's a growing kind of workshop on this, and there's the idea is kind of fuzzy representations rather than making a single argmax, right? So I think that on the one side it's a great idea. The problem is right now most of the data sets that we have haven't been annotated with enough annotators to know that. So to be able to kind of estimate the fuzziness of for training, you'd want to have at least for every data point several annotators probably to get this kind of, especially for subjective things like sentiment analysis where people don't always agree. It would be really nice to have that. The problem is that it makes annotation obviously that much more expensive. So you have to maybe triple, quadruple annotate everything you're doing in order to get a super interesting data set for that at least. And you have to think, one thing we haven't thought about very much, which I think it's starting now, is how to evaluate with that, right? Right now, whenever you're using F1 or accuracy, these are things that the community knows quite well, but once you get to start fuzzier kind of things, I think it's not something that NLP has worked with a lot in the recent years. But I think it's something that people are becoming more and more interested in. And I think that for things like sentiment analysis, it makes complete sense to start thinking about that, having rather than a single prediction, having let's say a distribution over possible predictions, and then also using that to kind of estimate how likely it is that our model is correct or not. Right? But thanks for the good question.
Thank you for your great talk. I have several questions. I even wrote them down to not to forget. Sorry. The first question is quite just to clarify. You say that the models are few short learners, so we need to make train sets smaller and depth set and test set larger. So how do you think we should actually generate this train set? Should we still be elaborate on what we are choosing to train, or we should do it randomly, like for example we do for the test set when we have large training? So just randomly split to train, dev, and test. But when we are few short learners, should we have less examples, but they still be versatile? So we should have a diversity, or it should be generated like randomly as well, because it's more important to have a large test set. So what's your opinion on that? Thank you.
Okay, thanks, good question. So my feeling about that is basically that I don't think that I thought too much about how exactly to set up the train dev test split. I mean, I imagine you could do like we do these days, just kind of randomly, but just making sure again that in the test set, that's where you concentrate more effort, I guess. Whereas these days, I feel like a lot of times what people do is spend a lot of time annotating for the train, making sure that everything's nice there. And then on the test set, that's kind of where you go, okay, we have a little bit left over, and that's basically it. Whereas this would be kind of just changing the thought process, I think, is making sure that you have a really good test set. And then the dev and the train would be, let's say, not an afterthought, but at least would take second priority after making sure that the test set is really good.
Okay, thank you. And when I first saw the title of your work, I thought about, okay, we are going finally to speak about how to do, for example, sentiment classification, not for sentences, but for text. So my next question is, what do you think about text and how should those texts actually be considered? Because, for example, when I guess everything that is expected from sentiment analysis, that when we read the text and we need to just to have like a score, okay, is it positive text, is it a negative review of something? So I guess, what do you think, how should the text be processed in terms of sentiment classification, for example? Thank you.
Okay, so I guess let me just make sure that I understand your question. Whenever what you're talking about is larger documents rather than just a sentence. Yeah, document level. This is, I mean, something that's been done quite a bit in sentiment analysis, at least, document level classification. And for me, it's still something that it seems a bit hard to put a finger on. So the data set we have in Norwegian, this Nurek data set, the original one is actually at all document level. And there's some interesting things that happen at document level, especially whenever you have self-reported, let's say these were star reviews basically from 1 to 6. And you have interesting things that happen. So you have very positive reviews word-wise with very poor star reviews sometimes. So for me, at least, the concept of doing things at document level is a bit complicated. Reviews. Mainly because the star, or let's say the final rating and the text a lot of times don't happen to coincide very well. So what I think might be more interesting is to kind of get this fine-grained version. And then after that, you can create a summary of that, which is quite interesting to kind of create a summary of points that are positive and a summary of points that are negative, because that's in the end what people want more than, let's say, just a single number. You want to know, what are the, let's say if it's a review about a restaurant, you want to know what are the good things, what are the bad things, right? I think that would be quite interesting.
Yes, thank you. That was exactly what I was thinking about by asking this question. And the last thing that, yes, we're speaking about ranking, and how do you think about ranking? So is ranking, in your opinion, better than just binary classification, or still we shouldn't just stick to those numbers and do something to elaborate, to work more on something that is going inside? For example, some part of the sentence are positive, some parts of sentence are negative. So should we think about ranking rather than binary, or really go inside the sentence? Thank you.
Thanks. Yeah. It'll still lead to the same general problem when you have, for example, two sentences that are 97% accuracy.
Yeah, because the most Okay, can you hear us? Can you hear us?
Here.
It's turned on.
Okay, let's move on with the question.
Okay.
So where were we? Okay, any other questions from the audience? I actually have some questions, but I will gladly give room for someone else. No. Okay. Yeah, I can just probably stand nearby. So yeah, you mentioned adversarial curation, and that was when you were talking about the annotation process. So can you maybe elaborate more on that? Like, where do you see the place for this adversarial curation, and how it should look like in your opinion, like on some practical example?
Yeah, I think for the one I was talking about was this Dynascent, which is done by Chris Potts and his group at Stanford. And their example, at least, was, I have it over here, actually. Let me see if I can get to it. Nope, I got it. Nope. Not further forward, actually. And here we go. So here was one example that they have. So what they do is they have this model in the loop. In this case, I think they were using Roberta Large. And what they try to do is they give them a prompt. So in this case, it was this year's NACL was very different because of COVID. And the model predicts positive. And if you trick the model, then it's kind of adapted into the new part of the benchmark. So it's a kind of constantly evolving benchmark. So it has the advantage of that it's always difficult. It has the disadvantage that it's kind of hard to compare sometimes between versions, right? I think what you could easily do is just kind of set cutoffs, once every 4 years and do like a version control kind of thing, right? Exactly. And I think that's what they're planning on doing as well, something similar. This works really well whenever you have something that's easy for people to see, again, at a sentence level. I think for structured prediction problems, you have to think a little bit more about how to present this to people and smarter ways to do it. Right now, I don't have a very clear idea of how I would do this, for example, for our data. I could imagine, for example, giving them only certain parts that they could edit. If you gave them, for example, the first one that I had here, this example, you could give them, say, you can edit the expression. Please try to make the model fail just by editing expression, or edit the holder. And there you have a little bit more control over what people are editing. And you can make sure that it's not too far away, but if it still manages to fool the model, then that would be useful. But it's going to be, I think the hardest part with these kind of adversarial ones is getting interesting new phenomena in there, right? So it's hard to direct them towards, let's say, some of the phenomena that would be, that you know you want to look at.
Thanks. And then the next question or comment is more general and more provocative, maybe. So since you were talking about going beyond the sentence classification in this or that direction, either towards document level analysis or towards like more fine-grained analysis, isn't it the case that it would be great to simply just drop or discard the whole notion of sentence in natural language processing, since sentences actually do not exist, right? I mean, in real language, we don't have sentences. We don't talk in sentences. We don't even write in sentences. Well, we probably sometimes write in sentences, but written speech, yes, but written speech is, of course, sort of not the direct manifestation of language. So yeah, we talk in clauses, in utterances, but not in sentences. So maybe it was like a mistake from the very beginning to even start processing, analyzing, and evaluating NLP approaches in the sentence level. So is there any advantage in staying on the sentence level besides its simplicity? Sorry for being a bit provocative.
That's okay. No. So no. my inner linguist, at least, is telling me the exact same thing as you, which is sentences are made up. Most of the time in speech, we don't speak in complete sentences. We don't use these kind of things. It's a very different kind of situation, right? And since, at least for me, the feeling is that all of kind of speech processing, NLP, vision are coming closer and closer together regarding kind of methodologies. Eventually, we're going to get to a point where we're working directly with speech rather than this kind of text, which we're doing now, or some kind of processed version of speech, which is going to be more interesting anyways, right? So yeah, I would agree that at some point in time in the not so far future, it would be probably interesting to just move away from sentences in general.
Feel free to say something.
Yeah, when I first saw the title, we were talking about that level. Yes, what I'm interested in. And your talk nails the summarizes the problems and the trends to solve them that exist in translation quality estimation, for example, very accurately, except where it doesn't go to the document level, because for translation quality, document level is probably the more interesting level. So when you were talking about going away from sentences, in translation studies, let's talk about segment, but there's a problem of how do you segment the segment. So if I can ask a question then, document level, how if you go away from sentiment generalize to other problems, what is the major problem with or processing?
So, I mean, for me, what I see as the main problem in lots of things is looking at what are the entities involved, what are their relationships, and what are the things that are going on, right? In the end, when we're thinking about, I don't know, the main difference between what we call sentences and what we kind of split it up into in a document is sentences normally have entities and they have a relatively simple relationship inside of that sentence. When you go to the document level, you have maybe lots of entities, you have lots of relationships between them. And right now, at least, we're not very good at dealing with all of these kind of relationships. You have things like, co-reference resolution, bridging, all these kind of things that we avoid basically at sentence level. But it's going to be super important to get better at these kind of things. And also just kind of think, I mean, I'm not so good at, let's say, document level tasks. I haven't looked at too many of them. But I have the feeling that there's a lot of these kind of phenomenon that we're still not very good at, and we don't have a good representation for the document right now, right? It seems like for sentences, we have kind of smaller representation we kind of deal with, but when we get to this document level, we don't have a good way of keeping all that information in and their relations together regularly. I think that would be something that'll be at least useful and important to kind of work on in the future. Yeah.
Anything else? Other? No, I checked, and there are no questions. Anyone else? Any other questions or comments or suggestions or anything? Nope. Okay. Anyone in the Zoom room? You can send your questions in the chat, or you can just unmute yourself and ask, just in case. And yeah, and if you are someone watching this talk on the YouTube live streaming, feel free to leave your questions as comments on our YouTube channel, and we will definitely yes, and we will definitely answer them later. And yeah, of course, follow our channel, put your likes, and subscribe. Feel free to follow us. But yeah, okay, so if you're absolutely sure that there are no questions, then you can still, of course, approach Jeremy. He's still with us today and tomorrow. So yeah, feel free to get in touch. And then I guess we can wrap up, and let's just thank Jeremy again. Yeah. And we now have time for lunch, and then we will meet again at 3, right? With the next session of NLP and something else in parallel. I'm sorry. SNA, yeah. Please check the schedule. Thanks a lot. Then we are wrapping up.
Dear colleagues, let me begin our new session on natural language processing, and I would like to invite our second presentation about software. Please open your screen and begin your presentation.
Sorry, did you say my name? I have some gaps right now, sorry. The Zoom is lagging. So right now me, yes? Mm-hmm.
Yes, please.
Mm-hmm. One moment. So do
I see your screen. Please, you can begin.
Okay, thank you. So hello everyone, my name is Kirill and I'm a data scientist in our research group. So today I would like to present our research project. So it will be about extracting software requirements from documents, specifically unstructured documents, but documents overall as well. I would say that this is a part of some bigger area that we are involved right now. So about like integrating and developing some products that could improve the experience of analytics, specifically of requirements and software requirements. Yeah. So sorry. So the whole presentation consists of several phases. So initially, I will explain our motivation, provide some example of our product, so what we like to see as our final step. Also, I will say a couple words about proposed architecture. Next, we move to dataset selection. So what the process did look like, and finally, I present results and make some conclusions. Sorry. So when we start speaking about NLP for requirements engineering, we see that this area is right now is pretty immature because the issues and problems right now can be seen on the surface. Requirements itself is pretty complex textual structure that in some cases do not have a direct definition. So sometimes we do not have like the full understanding of what kind of textual structure we're trying to extract. This is also related to some problems like writing style, spheres, areas, development, products, and other things. And it means that analysis could be error-prone and tedious for teams, especially if they are, for example, from different departments. Yes. And also we see that this associated with some technical problems. So right now it's very difficult to design some machine learning systems because there is a lack of ready-to-use data sets. And also there are not so many papers that could explain their experience about how they integrate, what did they do in order to automate the process of requirements analytics. And yeah, oh, sorry, this is not there. So what we'd like to see is it's pretty simple system. So we have some document, yes, and this document, requirement documents usually contain a lot of information which is not that relevant for us. So we'd like to extract only those sentences that are that contain only requirements or information about the developing product. But the problem is that it's a real mess. Usually it's a real mess in the document. Sometimes it's really hard to understand where requirements are located. Sometimes you could even have requirements as a part of some paragraph, or they could be separated in one paragraph. So yeah, and also, for example, numbering could be even different for requirements. So it means that basically the writing style could differ even on one page of the document. But still the task remains the same. So we want to extract only those relevant texts which are requirements. So those textual samples that explain something about the developed product, software product. Of course, there were some attempts. I wouldn't say that this is the same that we are working right now, but this problem about extracting abstractions. So this was probably very well-known problem in the past. So in these two papers, they were focused on extracting not requirements, but rather abstractions, because they were focused on extracting some word chunks, some structures. And only in a recent paper that was written probably a couple years ago, they were focused on the same task as ours, on binary classification task and on extraction, specifically requirements, and system that could distinguish between requirements and non-requirements. So the proposed architecture, we think that this should be very trivial and flexible at the same moment. So underlying architecture is, I think it's pretty well known. So we have just a document. We want to apply some system that could extract the text, recognize the document properly. Then we'd like to process this extracted text and split this into the sentences. Then we start working on extracting some features, some entities, in order to make some, in order to extract some vital, for example, descriptors, information or embeddings, and then we're just using them to solve our task. In our case, it's classification. Of course, any kind of project starts from, I mean, machine learning, sometimes NLP projects starts with a dataset selection, and this is where the problem starts. So as I mentioned before, this is a big problem right now. So there are not so many datasets that, and also if we're speaking about creating a system that could differentiate between requirements and non-requirements, this is even worse. So usually those datasets, they're badly structured. Sometimes even the classes presented in the datasets are not recognized by all companies or vendors. They usually are not open source because this is someone copyright of company. Of course, problems with all-purpose datasets, so they usually are very focused on their tasks and domain specific. And it means that the lack of practices mean that there is no qualitative metrics, no benchmarks, no so practice or some examples that you can rely on. Yeah, it means that it's tedious in making if you want to start such project, and you also need to remember that project is the data set of the project requires some goal setting. So in our case, it's extraction. So we, of course, made some analysis, and we found one probably the most relevant among other sets, which is called pure corpus. So this is something that is more about documents. So this is just a collection of documents, 79 documents, which includes requirement documents from and papers from different areas, companies. It means that it have a lot of lexicon, writing style, different lexicon, writing style, and other things that could help us to make a representative data set of requirements and non-requirements. So authors did provide some basic characteristics of their data set and compared it with the Brown data set, which is pretty famous, which is focused on modeling English language. So yeah, and then the process of preparation and annotation, I would say that this was pretty trivial. So of course they took most of time. So we manually extracted and processed each sentence in the documents. So and extracting both classes requirements and non-requirements simultaneously. We also use guidance if existed. So and utilized to make extraction more effective and to avoid some mistakes, to avoid some annotation confusions. And also we made some additional validation by our expert in our team. Assumptions during this extraction and annotation was pretty, I would say, widespread, so practice. Sentence was assumed as one data unit. Every list, sometimes requirements are written as a list, so we transformed them into a sentence. If it was possible, we corrected mistakes and repeated sentences were removed. Overall, we were able to process 30 documents and extract 7,700 requirements and non-requirements. Yeah, so what about the split? We decided to go for document separation instead of sentence separation. So we think that this condition is more relevant in practice in order to avoid situation when sentences from one document could appear in several subsets simultaneously. So, for example, if we start making sentence separation, then some text samples could be in the test, some in the validation, some in the train, and we decided to go for document separation and stick with 70, 20, and 10. So we try to achieve that, but yeah, with some some differences with what was planned initially. So this is the examples. They are pretty straightforward. So we have requirements on requirements. You see that these sentences have different lengths, sometimes different styles. For example, requirements could have some modal verbs which are probably the most vital feature, but sometimes it does not. So you see there is no modal verbs, and still it's a requirement which should be correctly classified. So results for pure, so we applied this data set in order to solve our binary classification problem for three probably famous architectures, FastText, Elm, and BERT. As it was expected, BERT showed the best results, but still the recall, as you probably see, because recall in some textual extraction tasks are more vital than precision, and it has the lowest one, which is pretty interesting. Yes, as our next step, we also made, I would say, extraction and classification for as a part of our collaboration with industry partners. So they provided us documents collection, where requirements were a bit different than we used to have them in the dataset or in the documents, because they were presented in the form of questions, and also those documents included mixed requirements for software and documentation. So usually we are focused on requirements of software development, but still there are sometimes requirements for documentation. So it might concern some constraints and some topics that are not covered in some data sets or not goodly represented in the data set. So for example, such topics as delay, length, and language, for example. But still, results were, of course, on the side of BERT, as you see. But right now, the difference between architectures is even bigger comparing with the pure dataset. And the recall is not that problematic right now compared with the ELMO architecture. Yeah, so this I would say our project, so our research project was focused on designing some model, some architecture that could focus on classification or extraction of requirements. So we did some work with dataset annotation. We created our own dataset and fine-tuned several architectures, including the advanced one, the BERT one. So we think that there is still some space for work, some space for improvements. We think that could be some details, there could be some refinements in the data sets and architecture. So we could try some new level architectures. And still, we also trying to implement this BERT. For example, BERT is already a part of our prototypes for extracting a bit different type of entities. For example, for security requirements extraction. Yeah, and it's already implemented. Yeah, it's working right now. Yeah, this is pretty the same. Thank you for your attention.
Thank you very much. Questions, please. So, a question from me: what can be other next steps? So we extracted the requirements. What we can do automatically with such requirements first? How maybe classify the requirements, or what we do?
Sure. So the initial goal, as I said before, so we think that this is supplementary model, supplementary architecture. Yes, so that so this is not our final solution, not our final result. So we want it should be used as a part of some complex systems. As I mentioned, we already implemented it for extracting security requirements. So this is I just explained, this is just a two-phase model where we have our fine-tuned BERT in order to extract and classify requirements, and then there is some more simple model that classify security requirements. Yeah, this is just one example. Also, this could be applied for some tasks as information extraction, because sometimes requirements is just a text, and sometimes we are interested in some chunks of text, some chunks of words. Yeah, and so there are plenty of ways how to use it.
Thank you very much. And now we should go to our first reporter. Please, Alexander. Now we are ready to hear you.
Раз.
Can you hear us?
We hear you.
Ладно, я могу здесь переключать, в принципе, ссылочку.
Мы еще не расширили.
So if there are again problems, I can go to our next presenter because first,
No, we're going to present because it's just 1 minute. It's fine. Okay. Hi, everyone. My name is Aleksandr. I am presenting the work language-free regular expression search of documents references. Can you see the slides?
Yes, we can.
Okay. What the motivation of the research? One can argue why should we extract references from the document? But actually, references can say a lot about the document, like you can adjust topic of the document by references. You can classify text reuse of legal or not if people cite if the text reuse is cited. So the next question is that huge amounts of scientific literature is written in English. So why do we need a multilingual perspective? There is a huge corpus in actually national languages like master theses, PhD, doctoral, and some national language papers. So we need to extract references of them too. And at the current time, this is done by like libraries manually. So the next concern is huge amounts of science is submitted via LaTeX with LaTeX source, so we can easily parse references from this. But for master, PhD, and doctoral theses, this is not the case. So we need to develop some technology. So highlights of the work. We develop an algorithm that takes only plain text as an input because usually it comes as a plain text without any layout or formatting. The method generalizes to multiple languages, and inference time enables to use it in high-load production. We compared performance with out-of-box sparse-seed solution and BERT-based lab-based C embedding approach, and comparison was done in transfer learning manner with in English, French, Russian, Chinese, and Japanese. And we found that proposed method is promising in terms of trade-off between generalization and inference time. So what's the intuition of proposed method? First of all, one can see that layout is potentially be important, but human can easily find bibliography by eye, even in plain text. So language is not important. If you take a look at document in language that is completely unknown to you, you can easily find bibliography actually. And the hardness of this task is you can't choose reasonable minimal classification unit. What should it like a sentence, text line? What is sentence in the bibliography? I don't know. Text lines are more or less reasonable. I will talk about it later. And also related data is more or less available in English. So we need to construct algorithm in transfer learning manner for English, and then transfers the knowledge to other languages. So what's about the data? there is no straightforward data for the task, so we synthesized one. We use synthetic English dataset. We sample 20,000 documents without bibliography from English Wikipedia. We sampled bibliographic lines from giant dataset, or the huge dataset of bibliographic lines, and insert them into document and remember where we inserted it. Almost the same routine was done for French, Russian, Chinese, and Japanese. And for final test, we used some small portion of manually marked up documents, master, doctoral, PhD theses available in open access for English, French, Russian, Chinese, and Japanese. What's the proposed method? Following the intuition, we somehow need to capture bibliographic structure. So we proposed 8 just regular expressions, but not language dependent, but language independent. We use special signs for any letter in any language and preprocessed data from all international variants of punctuation to one European analog. These regular expressions are not designed to match bibliographic styles because this is there are a lot of bibliographic styles, but we designed them to capture just something, and we believe that density of matches in bibliographic areas would be bigger than out of bibliography. And to force this fact, we designed match filter. When regex matches, we obtain a context of 50 symbols, extract 11 language independent features like counters of different punctuations, and assign a class label for each match, one if it falls inside the bibliography and 0 otherwise. We obtained like 8 million of such objects and just trained logistic regression on top of it. So one can see that the results for positive label are not so cool, but actually it turns out that this is sufficient because recall like a half, we lose half of important matches, but we filters out almost all not important matches. And once constructed for English, this classifier was used for other languages without any modifications. So this is an illustration of density of matches in the text. The horizontal axis is number of sample in the text, from which we take 500 symbols and calculate density matches for this window. So left, this is densities before filtering, and after filtering algorithm is a right picture. So one can see that we see we clearly see bibliographic area without any false positive during the text. So we can summarize proposed method like we find all regex matches in input text, filter out by filtering algorithm, compute density, find areas of high density, and if applicable, if we have bibliographic keywords for this language, we can adjust founded area. We choose symbolic precision recall and F1 measure as a evaluation metric. symbolic. This is because prediction and true are a list of predicted and ground truth intervals, like starting symbol, ending symbol. Again, learning and hyperparameter tuning was done on train and def, part of synthetic English dataset, and transferred to other languages. What are the methods to compare? Okay, we took BERT-based multilingual Loukachevitch embeddings, and if you consider text naturally divided into lines, we vectorize each line. We can assign class label 1 or 0 for each line if it falls or not into bibliography. Train logistic regression on top of it, and obtain such fancy results. We don't actually need filtering algorithm. BERT is cool in text line classification just as is. And we take parsit CRF based plain text classificator that was used as is. But what's the generalization for other languages? Numbers in brackets are for the case without keywords adjusting, and one can see that proposed method also generalizes, maybe comparable with BERT, and if we go to real documents, all of methods to compare failed because text lines are not so stable objects. Like if you trained on very long text lines, then your document is two-columned and text lines become shorter. Then distribution breaks and algorithm breaks. Oh. So, and if we take a look at inference time, this Loukachevitch BERT-based approach works. Ouch. Okay, BERT-based approach takes 1 second per document to process, but proposed method takes can process 30 documents per second. And in terms of generalization power and inference time trade-off, it is good solution to use.
Okay, thank you. I think that is last or not.
I'm sorry. Excuse me. We have some technical issues. So the last slide.
It's time to finish already.
Okay. In future, we propose to generate regex not manually but by genetic algorithms, such that every part of pipeline would be automated, and algorithm will be fancier. Thanks for your attention.
Thank you. Maybe one short question from somebody. I would like to ask about synthetic document. So you took a page of Wikipedia and add some reference section, yes, or
yes.
not? And should be some connection between document content and reference, or it would be there was arbitrary connection between references and the document. So what about thematic or something should be related text and reference or not?
Okay, I understand the question. This relation can take place, but actually experiment was how to distinguish structure of plain text and bibliographic text in multilingual perspective somehow, without consideration of relation, semantic relation of text and references. Just to capture differences in structure for multiple languages.
Okay, thank you. We should go to next presentation, and our next presenter sent pre-recorded presentation. Therefore, there is a suggestion to listen all the real presenter, and then only then go to pre-recorded presentation. So please I invite Maria Tikhonova to present her talk, please.
Hello, everyone.
Okay. So we can see your screen, and please begin.
So please let me know when it's possible to start.
Yes,
and
please,
how to...
Please begin, and we can hear you. We can see the presentation.
Yeah, can you hear me?
Yes.
Is the connection?
Yes.
Okay, so if there is any issues with the connection, please let me know, and we'll try to do something. So my name is Maria Tikhonova, and today I'm going to present you our work on continuous prompt tuning about the efficient automatic prompt search in the continuous space and how this method works for root GPT-3. But first, I'm sorry, how this thing works? Could you help me with the slides? Okay. Oh, yeah. But first, let me briefly remind you the background. Language models, in particular generative pre-trained transformers, has shown prominent abilities for many NLP tasks. And their adaptation to downstream tasks is a crucial part of the pre-trained language model's life cycle. The dominant approach widely used for this purpose is to fine-tune a pre-trained language model on each downstream task. However, fine-tuning large language models can be computationally expensive and time-consuming. Moreover, it requires large label training corpora, which can be hard to obtain. As a counterpart of this approach, a few-shot method has been proposed recently. In this setting, the model can only use the knowledge it acquired during pre-training, and thus can be applied without any gradient updates and fine-tuning. In particular, the model is expected to continue the text input consisting of multiple pairs of tasks and answer, and the last task with no answer. The setting when the model receives no training example is called zero-shot. This method has shown promising results in a wide range of NLP tasks. However, such an approach obviously has disadvantages, as long as the prompt has to be selected manually at this point, and the selected prompt may be not optimal. To illustrate this example, let me give you the example about tweet sentiment analysis, which show that even a slight change in the prompt format may significantly influence the result. For example, on the task of sentiment analysis on Twitter, additional opening or closing round brackets led to the increase in the score by 20%, which is a high difference, 70% and 90%. And since manual selection of prompt templates is obviously not optimal, the natural idea arises to search prompt automatically, and such methods have been actively developing in recent time. The pioneer in this field was the work prefix tuning, where the authors proposed to tune prefixes in the continuous space. The next work is GPT Understands 2, which focused on natural language understanding tasks and introduced a method called p-tuning, whose difference from prefix tuning was in that they used a BLSTM model as a reparameterization of the trainable embedding of the trainable prompt to enhance its convergence properties. Third article is a survey on all the previous methods where the authors have shown that LSTM is not necessary for the convergence. In our work, we follow the idea of the p-tuning method introduced in GPT Understands 2. We present a framework for continuous prompt tuning, or simply GPT, called RuPrompts in Russian. And we evaluate CPT on Russian supergroup benchmark for the RuGPT-3 large model. In addition, we explore the influence of the number of trainable LSTM parameters on the final quality, with the view that the number of trainable parameters can significantly be reduced and thus to speed up the training. We released our CPT implementation as a RuPrompt framework. It is a generic implementation of the continuous prompt tuning, supporting any Hugging Face compatible transformers, and can be used to adapt them to tasks using arbitrary losses. Let me now introduce continuous prompt tuning more formally. We will derive it from a few shot and zero shot concepts. Let us consider classification task and follow the generative classification paradigm, where the prediction for a prompt is inferred from the first token generated by a model after processing the prompt. The core element of all prompt-based methods is the natural language prompt, which combines a description of a downstream task with optional examples written in natural language. To illustrate this idea, let us consider the following example of a few short prompt for a machine learning task. You may see it in the slide. In this case, the prompt takes the following format, which you can see in the slide. Here we have pairs of queries or objects and targets. Note that the answer for the last instance is masked. We also have special elements such as task instructions, which explain to the model what is necessary to do. In other tasks, we may also encounter such elements as task and instance context. They're necessary in such tasks where the answer depends on some additional information, such as question answering, for example. Thus, the generic few shot format can be written in the following way, as it is presented in the slide. And the zero shot prompt format is basically a truncation of the few shot format. For example, let us consider the question answering task. And the example: Москва была основана в 1147 году на Москве-реке. Была ли Москва основана в 12 веке? And the answer is masked. Note that everything except The task instruction is usually derived from the dataset fields and cannot be changed. Task instructions, on the contrary, are defined by the task itself and thus can be trained. We use an auxiliary BLSTM-based model, which we call prompt provider, to produce trainable embeddings. Prompt provider has the following architecture. A sequence of trainable vectors is passed through BLSTM and then through a two-layer multi-layer perceptron with ReLU activation. Thus, we obtain embeddings for the soft prompt tokens, whose dimension is equal to the embedding dimension of the backbone model, and the number is equal to the total number of soft prompt tokens in prompt format. These embeddings are then inserted to the corresponding positions in the input of backbone and trained via backpropagation with the cross entropy loss. However, in this case, we calculate cross entropy only between the possible target labels. For example, if we have two labels, yes and no, then the cross entropy is calculated only between logits for these two tokens. Let me now switch to the experiments. We evaluated CPT for the Russian language on Russian SuperGLU benchmark, which is a natural language understanding benchmark, which follows GLU and SuperGLU methodology. It comprises 9 tasks, which can be divided into 5 categories: natural language inference, common sense, world knowledge, machine reading, and logic. We evaluated the applicability of CPT for the Russian language using our RuPrompts framework, and we used RuGPT-3 large as a backbone model and BLSTM model for a prompt provider. As long as we stick to the generative classification paradigm in our experiment, we regarded all tasks as binary or ternary classification. We compared CPT with its main competitors, with the fine-tuning and with zero-shot for RuGPT model. For the fine-tuning, we use Giant Russian framework, which is aimed at fine-tuning transformer models on Russian SuperGLU. And for the zero-shot, we used heuristically chosen handcrafted prompt formats, which sounded reasonable for each of the tasks. Training CPT on the task involves formatting its samples in a text line. In the slide, you may see examples for the NetQA, MuSRC, and RCB tasks, how each example in the task was formatted. In our experiments, we use sequences of 3 soft prompt tokens. However, it should be noted that the number of soft prompt tokens can be varied, and the optimal choice of the number is another area for the research. So, let us now discuss the results. You may see them in the slide, and it can be seen that CPT can be regarded as a strong competitor to fine-tuning and zero-shot. It outperforms zero-shot on 6 tasks and fine-tuning on 5 tasks. And thus, CPT allows to achieve reasonable model performance without any human assistant or computationally hard fine-tuning. In addition to the main line of the experiments, we explored how the number of trainable parameters in LSTM influenced the model quality. Our goal was to minimize the number of trainable parameters and thus to speed up the training. For this, we conducted a series of experiments on 4 Russian SuperGLU tasks, namely Parus, DNetQA, Terra, and RCB. We chose this task due to the size of the training corpora and as long as they are considered to be one of the most popular tasks among Russian SuperGLU. In this series of experiments, we varied LSTM number of hidden states from 1 to 1,536, and it can be seen that the number of hidden dimensions and therefore the number of the trainable parameters can significantly be reduced without significant decrease in total quality. For example, if we calculate the average of the scores for the 4 considered task, we see that the result for 64 hidden dimensions is only 7.5% worse, while it requires 360 times fewer parameters. In addition, as I've already mentioned, we released our CPT implementation as a RU-prompt frameworks, and now it is available on GitHub. You may see the link in the slide, and you may also install it via pip in Python. So it is available as a pip library. And at this point, RU-prompt supports through GPT models from the Hugging Face Hub, but can easily be adapted for other models such as RU-T5, for example, thanks to its generic implementation. Moreover, it can be adapted for a large variety of NLP tasks such as joke generation, detectification, simplification, and many others. In conclusion, in our work, we present RU-prompt's framework for continuous prompt tuning in Russian. We will evaluate continuous prompt tuning for Russian on Russian superglue and show that it is a strong competitor to standard approaches such as zero-shot and fine-tuning. In addition, we explore the influence of the number of trainable LSTM parameters on the total score and show that it can be significantly reduced without significant decrease in overall quality. As for our future plans, in the future, we plan to experiment with other tasks, namely with summarization, detoxification, maybe style transfer. And add the support of other models such as RU-T5, RU-BERT, and others in our RU-prompts framework. In addition, we are aiming to make a step towards the interpretability of the learned embeddings, and so we hope that they will become more interpretable. So, thanks for your attention.
Thank you very much.
That was all.
Are there any questions?
Yeah.
Can you go to the comparison table with other BERT settings, approaches, zero shot? Can you show the table?
Could you repeat the question, please?
It's not question. Currently, it's not. So one question from Andrei, please. Andrei, ask your question.
Yes. So are you finished with your question, or?
I'm not finished, but I should find a slide. But please ask your question.
Okay. So can you just click back again to the table with the results for superglue? Yeah.
Yeah.
Yep. So what I'm interested in is the scores for the Vinograd's schema dataset, RWSD. So the with the prompt tuning, you got 66.9, right? Did you examine the predictions?
Yeah, I know that here in this case, this is not like a fair case because most models, they like learn to answer the constant answer.
Yeah, so is it the case here as well?
Yeah, this is unfortunately the case here, as with many models which we see on on the leaderboard of Russian superglue.
Yeah, so essentially that's the majority class baseline. And that makes it even more interesting that without prompt tuning, the scores are different, which means that the model actually tries to predict something. So did you try to to study or to analyze deeper what the predictions are? Like,
to tell the truth, we haven't basically we haven't studied the predictions for the RWSD dataset because it's a hard dataset on which most of the models they converge to the constant answer,
Uh-huh.
and that's why we concentrated on other data set. But it's a very interesting idea, and maybe somehow studying the zero-shot answers, it will give us hint how to overcome this bound about 66.
Okay, so and the related
Okay,
question which I
sorry,
was,
sorry. I think that we should go to next presenter.
okay, we will talk more after the session is over.
So,
Thanks.
thank you for
Thank you.
presentation, and I would like to invite Leonid Sherstyuk for presenting his work.
Hello, can you hear me all right?
Yes.
Great. And do you see the slides?
Yes, please begin.
Great, so let's start. Welcome to the talk on context-based text graph embeddings for word sense induction. This work is done by myself, Leonid Sherstyuk, under the supervision of Ilya Makarov. So word sense induction is a task of assigning the sense to an ambiguous word, given the context. Consider two following examples. Mary went to the bank for a loan, and the bank of the river was covered with snails. The word bank is used in different senses here, and the word sense induction model should have to show that distinction. Sense induction tasks are closely related to word sense disambiguation tasks, in which the model has access to the sense inventory. Induction can be thought of as a clustering task, while disambiguation is a classification. In this work, though, we will focus on the induction task only. To solve the task, two approaches have been historically used. The first one revolves around carefully crafting word databases based on dictionaries and context crafting. WordNet and BabelNet both worth mentioning such databases. Another approach is to collect as much text data and construct co-occurrence graphs of the polysemic words. That way, sense is defined by more exhaustive context, but may be less accurate, as the contexts are processed automatically, not manually. Recent breakthroughs in natural language processing foster creation of complex models based on distributional semantics. From word to vec to BERT, language models are said to capture the sense of ingested text. It would be beneficial to use them for solving sense induction tasks. So in this work, we attempt to evaluate how effective would it be to combine more traditional approaches with novel text vectorization. We construct a preprocessing pipeline and evaluate several of its key parameters. With these variables, we parameterize 3 stages of our pipeline. First is calculation of embeddings, then processing of embeddings into graph data, and graph clustering. We will go more in depth on these parameters later. To evaluate our model, we used 3 datasets from word sense induction and disambiguation competition held as a part of RUS 18. Datasets cover an extensive domain of language. First is the active dict, dataset from the explanatory dictionary, which is based on a modern Russian language. Second is BTS RNC, dataset from the large explanatory dictionary, for which contexts for the dataset are sampled from Russian national corpora, hence the RNC. The last one is constructed on homonyms, which have separate articles in Russian Wikipedia. In each task, we are provided with a set of texts, all of which contain the same polysemic word. Our job is to provide groupings for each sense of that word. To evaluate the results, we use adjusted rand index. We borrow it from the competition. From the mathematical standpoint, rand index is quite similar to calculating accuracy, but on pairs of data points rather than just on data points themselves. And the adjusted part is the adjustment for chance. So on the graph, you can see our evaluation pipeline. Intermediate artifacts are in teal, and the preprocessing steps are in orange. Don't be afraid of its complexity. We'll construct it step by step. So first step is the generation of BERT embeddings. We use 2 models pre-trained by D. Pavlov on the Russian datasets. We assume that conversational model would work better with active dict dataset, while base BERT should work better on Wikipedia dataset. Up next is the way we reduce text embeddings. We need a single point in the embedding space to represent whole text, which will be used to calculate distances between different texts. That way, we can reduce every interaction of different contexts to 1 distance. So we devised we will talk about aggregation of text embeddings. So again, we need a single point in the embedding space to represent a text, which will be used to calculate distances between different texts. That way, we can reduce every interaction of different contexts to only one distance. And so we devised 4 ways to reduce our embeddings to that. And for each setting, we extracted last layer embeddings for every token of the text. So the first method is we are taking the target word embedding. Target word is the one that is polysemic. Secondly, we took mean of the whole context. Thirdly, we use single link distance between texts. So for each distance calculation between texts, 2 closest tokens are considered. And lastly, we use combination of first and third methods, taking mean between the target word and single link token. All right, let's move on. After aggregating embeddings, we perform several processing steps. So firstly, we optionally normalize embeddings. Secondly, several inverted distance metrics are considered to measure similarity between texts. Resulting similarity matrix then may be reduced, leaving only n closest connections. And finally, we optionally binarize adjacency metrics, reducing the resulting graph to an unweighted one, so only zeros and ones. After all the pre-processing, we cluster the resulting adjacency metrics using 1 or 3 algorithms which are most commonly used for the sense induction tasks. We just took what is usable in the space. So here is our full pipeline. I hope it's not so scary now. So let's move to the results. To evaluate impact of each setting on the final result, we took best models for each parameter value and compared the best and the worst of them. So for example, we can see that version of BERT played no role in evaluating on active DIC dataset. Best model for each BERT version yielded the same result. Same can be said for Cannon reduction, again for active DIC. We can also see that embedding aggregation and Cannon reduction are the most impactful parameters. The difference is the most dramatic for the Wikipedia dataset. So on the next slides, we will actually see actual final scores and delve a little bit deeper into 2 of these points. Our combination of target word and single link embedding has worked the best on 2 or 3 datasets, closely followed by the target word embedding. We can see that BERT added enough context data to the target word embedding for it to be useful in clustering, but single link shift works just a bit slightly better. While Cannon reduction had no impact on active DIC dataset, it significantly hinders the result on the other datasets. But at the same time, binarization of similarities tend to help clustering, which is unusual. By binarizing, we are reducing the information available to the algorithm. Impact analysis of the other factors may be found in our paper. So here we present best parameterization for our models for each dataset. BTS and Wikipedia datasets are evaluated best by the same model, which differ only in clustering algorithms, which may point to the importance of the actual clustering algorithm for this task in this setting. Active DIC may be considered as an outlier here, disagreeing on every single parameter. Our experimental pipeline managed to beat one of the baselines presented at the competition. We consider that a great result, given that we didn't even pursue that goal, and our pipelines requires no training. So to conclude, we consider our research successful exploration of merging graph clustering and BERT vectorizations to solve sense induction tasks. We evaluated multitude processing parameters and discovered several important ones that are given in bold on the right. We hope that our study would foster research and creation of production-grade solutions for solving sense induction tasks with little to none training. I thank you for your attention and will be happy to answer any of your questions.
Thank you very much. So it seems that there is some question. So how did you form the bird embedding for the target word in cases when it's representing by several tokens? How many contexts you considered for each word? So the question several tokens for target words and context for each word.
I do understand the first one. We just
several. You can yourself see in chat. So when word is presented by several tokens.
Okay. As for the embedding of the target word, we wanted for it to be a single point, so we took a mean of that if that was the case, that there is more than one target word. As to how many contexts have we considered for each word, I don't really understand the question, because we can just go back to the point where we try to reduce it to a single, let's say, entity, and every dot here represents a single token, embedding of a single token. So the whole cloud represents a single context, and we should score somehow every of such contexts. And it should be clustered one way or another. So maybe I didn't understand the question.
Maybe the answer is that you took all contexts from the dataset, and the dataset provided some context, so you used the whole number of sentences, maybe.
Yeah. Sorry, I didn't elaborate on that data format. So basically, it's some kind of a sentence, maybe set of sentences, in which there is used some words that we need to induce the sense of. So, like, we actually can consider this slide as a kind of entry from a data set. So we are giving precisely that, just several sentences in which we are told which word is the target one. And so we just have to somehow cluster all of these sentences into groups with same sense. Yeah.
Okay, thank you very much, and we should go to next presentation.
Yeah.
Please, Елена Разова, Сергей Вычегжанин, Евгений Котельников. Evgeniia, are you with us? Okay, we can see the presentation. You should, okay.
Okay. Good afternoon, dear colleagues. Do you hear me?
Yes, please, you can start.
Okay. Okay. Good afternoon all the time, dear colleagues. I would like to tell you shortly whether BERT looks at sentiment lexicon. The main approaches to sentiment analysis are lexicon-based or rule-based methods and machine learning. In particular, deep neural network models with the transformer architecture like BERT. The lexicon-based methods are high-speed, easy to implement, they don't require training data, and the long learning process, and the results are easy to interpret. However, deep learning models achieve state-of-the-art results in sentiment analysis. But why? What is the difference between deep learning and lexicon-based methods? What do deep learning models know that rule-based methods don't know? And does BERT look at sentiment lexicon? This last question is a goal of our research. The key idea of our study is as follows. We state a hypothesis that BERT-type models pay different attention to sentiment and neutral lexicons. To test this hypothesis, we evaluate the difference between the distributions of attention weights of sentiment and neutral words with the help of Kullback-Leibler divergence. In our experiments, we used 3 Russian language corpora annotated by sentiment: Romip 2012 News, Sentiroval 2015 Banks, and Ru Sentiment. We chose these corpora because, firstly, they differ in the type of texts, and secondly, lexicon-based methods show significantly lower performance for these corpora than neural network models. For analysis, we used fine-tuned Rubert model from DeepPavlov. To create sentiment dictionary for our research, we combined 9 publicly available Russian sentiment dictionaries. They are listed at the slide. We used voting procedure. The final dictionary included only those words that are included in at least 4 source sentiment dictionaries. For the analysis, we use the following algorithm. The first step is to build an average attention matrix and find weights for each word in the text. We take attention weight matrices for each head at the last layer and merge divided tokens. Then we average weights for each word and lemmatize all the words. As a result, we obtain the attention weight for each word for a given text on a given attention head. At the second step, we calculate the distribution of attention weights for sentiment and the neutral words of the corpus. On this diagram, we show that the distributions of attention weights for sentiment lexicons, these are green, red, and the blue lines, differ from the distributions for neutral lexicon, black lines. And to confirm it, we sampled random subsets from neutral lexicon, yellow line. It turned out that the attention weights distributions really differ for sentiment and neutral lexicons. At the third step, we calculate the Kullback-Leibler divergence as distance between the distributions of attention weights of different word sets. Then we test the significance of differences between these distances with the help of Wilcoxon-signed rank test. The results show that there is significant difference between the attention weights distributions of sentiment and neutral lexicons for 75% of the cases. This is 2 pluses situations. This situation is the same for all 3 corpora and for the most of the attention heads. It's interesting that the head number 7 for all the corpora highlights sentiment words. We also looked at some examples of how attention weights to sentiment words affect the final decision of the model. In the first example, from the Ru sentiment corpus, Rubert pays maximum attention to the sentiment positive word chic, шикарный, and the classification result coincides with the true label. However, in the second example, Rubert also pays maximum attention to the positive word cool, прикольный, but decides on the neutrality of the text. But true label is positive. So despite the high attention weights to sentiment words, Robert doesn't necessarily make the final decision based only on them. So we propose a new interpretation method to analyze attention weights distribution for sentiment and neutral words. We conclude that 75% of the heads on average pay more attention to sentiment words than neutral ones. In the future, we plan to extend the sentiment dictionary to conduct a similar study on other sentiment corpora and to examine attention on different layers. Thanks for your attention.
Thank you very much. Other questions? So I would like to ask that, in fact, we can be sure that many real sentiment words and expressions were not included into existing sentiment vocabularies because sentiment is context dependent and domain dependent. Therefore, some words you consider as neutral, in fact, they can be sentiment words. Yes.
Yes.
How to it can be overcome only if you annotate all words in sentences that can be sentiment in the context. So yes, to be exact, to provide precise comparison. Yes, with sentiment and the neutral words, we should annotate all words in sentences. No. No.
On the one side, yes, of course, yes, but like SST corpus, do you know about sentiment debunk corpus? Yes, of course, but I think this is not so necessary because we took I think very good dictionaries, sentiment dictionary, because this is some kind of a compromise between completeness and precision of this accuracy of these lexicons. We took a voting procedure for 9 sentiment dictionaries. So we hope that this dictionary is precise enough. And I think if we will take, for example, I know 10 or 15 corpora, sentiment corpora, we will obtain some statistically significant results, I think. So this is our way. I don't know.
Mm-hmm. So maybe it was possible to find, for example, positive or negative documents where sentiment words, for example, were missed. Therefore, maybe additionally to annotate them with the words. So there are some questions from Mikhail Tikhomirov.
I see.
Please answer your question.
Have you tried not averaging but maximum when creating attention distribution? Maybe some layers looks at lexicon, but others not. We took just right now. We took just last layer. This is the 12th layer in the bird, in the Rubert. So this is just last layer, and of course we thought about not averaging, but maybe more precise, but not maximum, but individual weights for words. Averaging or maximum, I don't know what is the difference. Maybe yes, maybe this function, yes, kind of function is also important. I think yes, of course.
So I think that there are somebody from the room can ask question. Irina.
Yes, it's actually me.
Ah,
You hear me, right?
yes,
Yes, Andrei,
okay.
yes, yes. I
Yes.
see.
So, yes, thanks for the interesting talk. Maybe I missed it, or maybe there are more details in the paper. But can you give at least some summary of the differences that you found between the different lexicons that you studied, or were there any differences? I mean, can you just yeah, I saw I remember this table, but can you summarize it a bit?
We have important things here is two pluses. First plus is the difference is not random, so the attention is not equal to sentiment and neutral. And the second plus is the attention to sentiment lexica is more than to neutral ones. So if we have two pluses, this situation where this head pay more attention to sentiment lexicon. These two pluses, green pluses, to positive lexicon. Okay?
But it is not differentiated across different lexicons, right? It is not different.
We took just one sentiment dictionary. This we used.
Okay, so you used only one. Okay.
Yes, just one. Yes. So and 75% of the heads pay more attention to sentiment or positive or negative lexicon.
Just that, wouldn't it be interesting to sort of to analyze separately, to do the same separately for each of the dictionaries that you used without merging them into one?
This is some kind of very hard work, I think, because we have 10 lexicons. So I don't know. Maybe yes, but I don't know. Thank you for your question. Yes.
Okay, thank you very much for your presentation. And now I think we should switch on the pre-recorded presentation, and it will be our last presentation. I try to somehow to switch, but sorry, I try to. Okay, I can't, okay, try to, okay, so I'm going to, so can you see a screen from, please?
Yes, we can.
Okay,
yes.
so I try to,
Can you please make it louder?
Louder, but it's not,
The sound is not very good.
but I'm not sure that it depends from me, but maybe from initial.
Because you're speaking very loud here and the presentation is very quiet.
Yes, but it was pre-recorded, and I'm not sure that it's my site.
Okay.
So I do not know what to do.
We can
maybe
also try
I
if you
can.
want.
But 100% here for.
We can also try to launch. We can also try to start the video. Yes, we can run. Can you stop sharing? Yes, I guess, yes.
Due to lack of labels for speech and data, we utilize adversarial attack to imitate speech.
portions of people that use code switching in their speech are unknown. We considered only attacks that suppose embedding on one type of code and replacing them with their substitutions if it increases the model's loss. First, like word level is effective replacing single words with translation. This makes a radical drop. The second attack, phrase level, consists of building alignments between a sentence and its translation. So we can replace the token with its alignment substitutions. We've also suggested an adversarial pre-training method that increases the model's quality on adversarial input data and, as a consequence, on real code switching. The method consists in generating an adversarial training model in a math language model.
Sorry, I understand that no sound from me from the presentation, and yes, and maybe try to again.
In our paper, we've researched disastrous drop in performance for all the models. After the phrase level, the drop in performance is not radical, but still very huge. That suggests that the adversarial pre-training defense method increases model performance.
So sorry, I think that maybe to
This paper shows an adversarial attack on the single task-oriented dialogue system.
So I think maybe maybe I will load this presentation to the chat and because it's impossible to reproduce. So I don't know, maybe chat to write.
We will now send it to the Telegram chat.
Telegram chat. So I think that maybe not. It's no sense to send to Zoom chat because it will be closed. Maybe please send the presentation to the Telegram chat and finish the session. For session, for listening, for questions. So let's meet somehow offline together. So bye to all.